Hey guys, welcome back to another video. This video is going to be a full crash course of the entire A2 level physics syllabus. I'm going to cover the important parts of all topics from the syllabus and hope you do well in your upcoming physics exam, right? And this video, I'm going to start with circular motion. That is the first topic of A levels. And by the way, this topic doesn't individually come in the question paper usually. Sometimes it has in the past years, but this comes usually integrated with topics such as gravitational fields and oscillation. So, okay, fair enough. Now, let's start off with the basics of circular motion. In general, you need to know that this is your center, this is your radius of a circle, and this angle at the center is going to be theta. And for this, we're going to consider this theta to be in terms of radians, right? You know the difference between degrees and radians by now. I mean, you should at least. So this arc length, this distance on the circle is known as your arc length, right? Fair enough. Now, angular displacement, what is the angular displacement? Between 2 points, what is the angle between? Angular displacement, right? Nothing else. Second thing, this formula, S is equals to R theta. You should know this from maths. S means your arc length. R is the radius from the center to your circumference. Theta is the angle at the center, right? Now, defining radian. What is radian, right? What is radian? Radian is, or 1 radian specifically, is the angle subtended at the center of the circle where its arc length equals to the radius. What does that mean? That whenever your arc length is exactly equal to your radius, you know the angle at the center should be what? Should be 1 rad. Similarly, if you have your arc length to be 2, the radius should also be 2 for your theta at the center to be 1 rad. Now, if they ask you to define what 1 radians is, this is the definition you're going to give. Now, in terms of degree, 1 rad is going to be 57.295 and so on degrees. Second thing, you need to know angular velocity. What is angular velocity? As the name suggests, it's the velocity at which the angle changes. Hence, rate of change of angles. How fast the angle is changing. Rate of change of angular displacement. Angular displacement means angle between 2 points. Fair enough. Now, I can say omega or angular velocity is d theta by dt. That means for any change in theta, how long that change took. It is also equal to 2 pi, that is the entire, circle. The degree of the entire circle is going to be obviously 360 degrees or 2 pi in this case. So 2 pi divided by time period, that is how long one point took to come back to the same point by rotating by 2 pi radians, right? So 2 pi, the entire degree divided by time period, how long it took for the entire journey. That is also a way to find out your, angular velocity. Now, the unit for this is going to be rad per second. Because change in rad, change in time, rad per second. Fair enough. Third thing you're going to learn about is linear or tangential velocity. When, let's say, let's consider for this to be a uniform circular motion where the force is always same at the center, towards the center. When you have anything moving in a circle, let's say, notice one thing, the magnitude of speed in uniform circular motion, the magnitude of speed or speed, since it is a scalar quantity, is never changing, right? The speed remains constant. However, one thing is changing, velocity. Why? Because its direction is changing. The direction at every instantaneous point is changing. At this point, moves upwards, has a tendency to move upwards. At this point, has a tendency to move in this direction. However, since it is connected to, let's say, this pen or any rope, let's say, it can't move in that tangential direction, right? So, there's a force towards the center, right? That is centripetal force. Fair enough. Now, this tangential velocity, right? How do you find that? You know S is equals to R theta. Do you know S is equals to R theta? Yes, you do. Now, can I differentiate both sides? Yes, I can. If I differentiate the distance, ds by dt, it's going to be velocity. If I differentiate with respect to theta over here, that is going to be angular velocity, r omega. Now, what does this mean? This equation is basically telling you for, let's say, very small change of theta from point A to point B, right? From point A to point B, this small change in arc length, let's call this 0.001 meters. What was the change in theta? Let's say it was 0.5 rad. Let's say the change in radians was 0.5 rad. Now for this 0.1 meters to change and for this 0.5 rad to change, both for the same motion of particle, how long it took? Right? Now when you differentiate both sides, it is going to give you velocity in terms of radius and angular velocity. Now when you multiply your radius with angular velocity, you're going to get your tangential velocity, right? That is your tangential velocity. This is how we find out tangential velocity. Now look at this animation. So both particles are moving around, right, in a circle. Notice one thing, both of them have the same angular velocity. However, difference is their distance. Blue has a greater radius, pink has a smaller radius. Hence, to cover the same 2 pi, that is 360 degrees, blue one has a higher velocity. Notice, twice the velocity. Why? Because V is equals to R omega. If your radius is twice as much, your angular velocity will also be, tangential velocity will also be twice as much, right? Keep that in mind. Fair enough. Now, second part of this circular motion chapter is going to be centripetal force and acceleration. As I mentioned, your tangential velocity, the direction is changing, is constantly changing at every other instantaneous point, it is changing, right? Now, I know velocity is a vector quantity. Direction of velocity keeps changing over here. Now, due to this velocity changing, acceleration is our change in velocity. Hence, there is an acceleration. Due to this change in velocity, there must be an acceleration, right? That is what we find out. Acceleration is change in velocity over time. Since there is a change in velocity, and when you find out the vector, right, when you break down the vector, the components of the velocity, you will find there is indeed a change in velocity in a specific direction. And when you work with that, you're going to come to a formula for acceleration. So there are specifically 2 formulas for acceleration, right? One is acceleration is equals to v square divided by r. This derivation is sort of explained in my full playlist about circular motion. But anyways, all you need to know is that velocity square or tangential velocity square divided by r is going to give you the acceleration towards the center. That is, of any object in circular motion, that acceleration towards the center can be found out by its tangential velocity square divided by the radius at which it is rotating, right? Now, when you plug in this formula, that is V is equals to R omega that you already found out up top, you can plug this in instead of V, and what you get is acceleration is equals to R omega square. How you ask? R omega whole square divided by R, hence R omega square, right? Fair enough. Now, to find centripetal force formula, you know F is equals to ma. F is equals to ma. Now, in this formula, you can substitute acceleration, that is V square by R, V square by R. Hence, I get mv square by R as our formula for force, net force. That is centripetal force acting towards the center. Now, the other thing is, I can also substitute V is equals to R omega over here to get a more suitable formula that is more useful in case of, let's say, oscillations, no, not oscillation, but gravitational fields often. That is mr omega square, right? So you substituted the velocity with r omega. So what you get? mr omega square. So these are your formulas for acceleration and centripetal force. Now, a few examples. Let's say you're rotating this bucket in circular motion, vertical circular motion. There's a tension that is towards the center. This tension is acting as or contributing to your centripetal force. That is the force towards your center. So you're pulling the bucket towards yourself, hence its velocity is changing, the direction is changing. In case of cars moving around, notice one thing. You may ask, where is the centripetal force coming from, right? The centripetal force is actually towards the center, but where is the force coming from? Look at this example. Let's say I have this hand. I do have this hand. So this hand is, rubbing against the other one. The wheel, let's say, is, is facing friction against the road. So let's say it wants to turn this way, right? It wants to turn rightwards. It wants to turn rightwards, right? It wants to turn rightwards. Fair enough. Now what happens is when it does turn rightwards or moves, right? Moves, the tire has to move leftwards. The tire has to move leftwards for the car to move rightwards. Notice one thing. When my hand is, let's say, rotating leftwards, what's happening is the road is applying a force rightwards. Because from Newton's pair of forces, you know that whatever force I apply on the road will apply the same magnitude of force but in opposite direction. So when my tire is rotating leftwards, this hand or this road is applying friction rightwards, which is why the car is able to turn right, because the force is exerted towards the center, while the tire is moving exactly in the opposite direction against the road. And the road with friction is applying a force towards the center on the car. Hence, every time you take a turn, this is why you can take the turn, because friction is acting towards the center with respect to where you're taking the turn, the arc. Fair enough. So in these cases, just understand, I gave you a weird example of how the friction works and how it is acting towards the center. But if you can visualize it, or if you can take an example, you would better understand. Now, third case, let's say satellite, geostationary orbit. If you know from gravitational field, in orbits, there is force, attractive force, gravitational force. This acts as a, centripetal force. Now, this one, where it is going to, fall in a circle or an arc, there is a force towards the center that is its own weight. Great. Now, we know these formulas. These are going to be very, very important: centripetal force formula and acceleration formula. Now, resolving forces in horizontal circles. Notice one thing. Should I clear everything out? Yes, I should. Notice one thing. This car in a ramp, let's say in circular motion, but elevated by this ramp by degree theta, right? So now perpendicular to this, I was going to say truck. Is it a truck? No, car. So perpendicular to this car, this normal that I'm drawing, perpendicular to the slope or normal to the slope, the weight acting downwards, notice acting downwards, and there's a reaction force on the car acting in this direction. Compare this arrow. In the direction of the arrow, normal force is reacting due to these tires coming in contact with the ramp. These are contributing to your normal reaction force, right? Now notice one thing. Don't you think there's an imbalance of force over here? The forces are not cancelling out. And when forces cancel out, they are in equilibrium. But over here, forces don't cancel out. Why, you ask? Notice one thing. For this normal force that is exerted on the car, there's a component in this direction. Notice one thing. Component in this direction. Why can't I draw a straight line? Component in this direction. This is still not a straight line. Good. Yeah, component in this direction, right? Upwards, horizontal component. Now notice one thing. You know your car doesn't move up and down, right? When it's going around in circles, the car is not dancing up and down, right? Hence, there is no sort of resultant force in the vertical direction. Hence, you know, if this is theta and this is also theta, that means this theta degrees. I have to show you, geometrical proof to make you understand that this is also theta. Just believe me and understand that this is also theta. So considering that, if this is also your theta, vertically opposite angles. Hence, you know n cos theta, that is considering this theta, n cos theta, this component, n cos theta, that force is supposed to be exactly equal to your mg. Exactly what? Equal to mg. Why? Because you know the car is not dancing up and down. There is no resultant force on the car up or down. Hence, n cos theta, or the normal reaction forces component that is vertical in direction, should exactly be equal to your mg, because both vertical forces should cancel out, right? So n cos theta is equals to mg. Second thing, this n sin theta now, with respect to this theta, n sin theta should be what? Notice there is no resultant force in this, no force in this direction to balance it out. No force in that direction. Because weight is over here, reaction force is up there, there's no force in this direction. So this n sin theta should be your centripetal force. Should be what? Should be your centripetal force. Now, also understand that in these cases, we don't consider friction. Why? Because then the calculation gets far more complicated. So we consider this to be a frictionless surface usually. Anyways, your n sin theta, notice one thing, n sin theta should be your centripetal force because it is acting directly towards the center. So let's say a car is moving around a ramp, on the ramp. The reason it is, able to move on a slanted surface that does not have a friction. Notice, there is no friction, but the car is able to move, slanted, elevated on this ramp without falling down towards the center. Why can it do that? Because of maintaining circular motion at the optimal velocity. Since there is a centripetal acceleration or centripetal force towards the center. That is the only reason why it can remain in the circular motion. It has reached such a velocity where it is able to continue moving in circular motion, right? And we'll understand about what that specific velocity is going to be. But anyways, you now know in these cases your n sin theta normal force times sin theta is going to be centripetal force. Fair enough. Yes. So you can break this centripetal force down as mv squared by r, right? If let's say you know theta normal force, let's say they're asking you to find the velocity, you can do so, right? Fair enough. Now another example, this is going to be this bob attached to the ceiling, moving in horizontal circular motion. In this case again, notice your t sin theta or tension in this case it was normal. In this case it is tension. Tension is helping the bob or object move around in circles. So this tension is allowing centripetal force towards the center. Notice t cos theta, that is upwards, is exactly equal to again your mg, and your t sin theta, t sine of theta is going to be in this direction. That is going to be what? That is going to be your centripetal force, right? T sin theta unbalanced, hence t sin theta centripetal force. T sin theta I can break it down as mv squared by r, because centripetal force formula, what do we know? Mv squared by r. Now t cos theta, which is balanced by your weight, is t cos theta is equals to mg. Now when I divide sine by cos, or 1 by 2, equation 1 divided by equation 2, notice t cancelled off, sine by cos is going to be tan theta, and mv squared by r divided by mg is going to leave you with v squared divided by rg. V squared divided by rg. Fair enough. So this is an important formula, right? So you don't need to memorize this. When you have any situation, you can derive the formula, but I'm just showing you a case. Now for vertical circular motion, where vertical circular motions are never actually uniform circular motion. What I mean by that is, in uniform circular motion, let's say horizontal circular motion, there is a force that you're exerting, let's say tension, but on this pen, you're making this rotate, is a tension, right? Now you can keep the force constant, the tension constant, keeping the centripetal acceleration or force always constant. However, in vertical circular motion, notice one thing. When this pen's position is at the bottom, mg is acting downward, weight is acting downward, and I'm pulling the pen upward. Because in this position, the tension is towards the center, but the mg is downwards. Hence, both are in opposite direction. When it is upwards, there is mg downwards and tension is also pulling it downwards. Hence, there is a difference in force, difference in amount of force and its direction, which is why in these cases, centripetal force is not constant. Hence, centripetal acceleration is also not constant. Hence, it is not uniform circular motion. Now, in vertical circular motion, let's analyze two positions. One is the topmost position, case 1, where your net force is the sum of mg and your tension, right? Now, in this case, notice F net, that is your sum of centripetal force, is going to be mg acting downwards plus your tension also acting downwards. This is one of your formula. Now, case 3, where tension is pulling it up, but mg is acting downwards, you're going to say F net is, that is the net force towards the center is T2, that is tension, in this case, in this position, tension pulling it up, minus mg that is acting downwards. Hence, you can make tension the subject and say mv square plus mg, right? In this case, if you make tension the subject, it would have been mv square by r minus mg, right? Fair enough. Now, what are the observations of these two position 1 and position 3? We can say tension 2 is greater than tension 1. How can you say that? You can say that since your T1 is the difference between mv squared minus mg. However, your T2 is mv squared divided by r plus mg. T2 is the sum of both, whereas T1 is the difference between both, which is why obviously the sum is going to be greater in amount. Hence, T2 should be greater. Your tension when at the lowest position should be greater. Now think of this logically. It is supposed to be greater. Why, you ask? Notice one thing. A, the ball or any object is going to pull the string down, right? It is going to create tension either way. If I don't even apply extra force on the string, there still is going to be a lot of tension in the string due to the object's weight. Now, if I also pull the object, obviously there is going to be greater amount of force, right? Now, in topmost position, there is a greater amount of chance that the string will get slack. Why? Because I have to pull the object with greater amount of force since this object that is up there has a weight acting downward. Hence, if the object is successful in coming down, the string will get slack. Hence, I need to create such a velocity that the object cannot fall down. The moment the object has a tendency of falling down, the string gets slack, meaning there is less amount of tension in the string. Being slack means there is no tension in the string. However, at the lowest position, there is always tension in the string because weight is pulling down. It is stretching the string. In the topmost position, it is getting flat, which is why we can even theoretically say T2, tension 2 is greater than tension 1, where tension 2 is the lowest position tension and tension 1 is the topmost position tension. Now, for the minimum speed, which would be at the topmost position for tension 1 to be 0, T1 should be 0 to get the minimum speed. Now, what I mean by that is basically T1, this formula, if you consider, T1 is equals to mv squared divided by r minus mg. Now, I was talking about something previously, that is how to find out the optimum velocity at which any object should rotate or be in circular motion such that it doesn't fall down. Meaning, let's consider vertical circular motion. In this case, at what velocity should the object rotate such that the string doesn't get slack over here? At what velocity should the object rotate such that your circular motion is maintained. Now, to find that is in case of our worst case scenario, that is topmost position, where there is greater amount of chance that the string gets slack, I have to consider that position. Where I'm going to consider, let's say, the tension gets instantaneously slack. That means tension is 0, right? I'm not considering it negative, I'm considering it to be 0 as an instantaneous point at the topmost position. And at this position, I'm going to find out the velocity. I know the mass, v square divided by r. Take mg on the other side, that is mg. M and m is going to get cancelled off. And your velocity is going to be g times r. V is root over g times r. If you make v the subject, your your velocity, optimum velocity for being in vertical circular motion will be given by gravity times radius under root, right? This is going to give you the exact velocity at which instantaneously the tension will be 0. Meaning it won't fall down, but at that point instantaneously tension will be 0. That is the lowest possible velocity at which you can have vertical circular motion of the object. If the velocity is greater, fair enough, great. The tension will be greater, hence less chances, no chances that the object will fall down or get the string to be slack, right? There is no chances that the tension will be 0 in that case, if the velocity is greater than root over g times r. This is very important, keep this in mind. You don't, again, need to memorize, keep the concept, you can understand. Fair enough. Tension 1 should be 0 to get minimum speed, fair enough. For maximum speed, T2 max, the max force that the string can withstand. Now, what I mean by that is, let's say, to find out the maximum tension that the string can withstand, basically it is the maximum force that you can exert on the string. So let's say if the string has any upper limit of max amount of force, that is also going to be the max amount of tension that you can apply in the circular motion. Not needed. Anyways, moving on, contact forces in vertical circles, right? So you can have another object inside the object in circular motion. Let's say I have a container. The container contains a lot of biscuits, or let's say in this case, a lot of springs. Now, if I rotate it, or if you have seen this example multiple times in videos, right? If you rotate a water bottle, what happens is the water tends to, stay stuck with the bottom position. Always, it's going to stay stuck with the bottom position or the bottom face of the water bottle. Now, why does that happen? That happens due to laws of circular motion. Now, understand that in this case, let's say vertical circular motion, this F net of the spring, the net amount of force on the spring is going to be, or in this case, if I talk about the net amount of force on the water itself, the amount of water in the water bottle is going to be mg. Let's say in the topmost position, if my water was over here instantaneously, what would be the forces acting on it? A, mg acting downwards, that is weight of the water acting downwards, right? Fair enough. Second thing is the reaction force, that is between the water and water bottle surface. The water bottle surface, when I am in circular motion, this face of the water bottle, that is the bottom face of the water bottle, will exert a force on the amount of water or volume of water inside. That is your contact force between the water and water bottle. That contact force will also act downwards. Hence, your total force or centripetal force for this water is going to be mg, weight of water, plus reaction force. Both you add together, you're going to get centripetal force. Now, if you want to specifically find out what amount of force is the water bottle exerting on the water, you make n the subject. You make n the subject, where n is now going to say Fc, centripetal force, minus mg will give you the normal reaction force between water and water bottle. Fair enough. Now you can also plug in the formula for Fc, that is centripetal force. Now notice one thing over here. At the topmost position, if your velocity decreases, that is velocity at which you are rotating the object, rotating the water bottle, your reaction force also decreases. Now logically think about this. If you rotate this water bottle at a slower speed, chances are the water is going to fall down. The water will not stay stuck with the surface of the bottle, right? Now if you rotate it faster, what happens? There is greater amount of chance that the water will stay stuck with the bottom of the bottle, right? Why? Because in that case, V is greater, hence mv square by r is greater, and mg stays constant, hence your normal force is greater. Understand that carefully, right? Understand that very carefully. Fair enough. So, as you increase the velocity at the topmost position, the amount of normal force will increase. Now, other case scenario is lowest position. At the lowest position, what's happening is the weight of water is acting downward, normal reaction force is acting up. So, your net force will be normal reaction force acting downward and, normal reaction force acting upward. Normal reaction force on this acting upward, that is normal reaction force by the container on the water acting up, and your weight acting down. Hence, your F net is going to be N2, that is force acting up due to the reaction force, minus your mg. Now, when you make the normal reaction force the subject, you're going to get centripetal force plus mg. Hence, your N2, again, in this case, this position, N2 is greater than N1. Just like the previous case, your T2 was greater than T1. That is, in the case that the object is at the lowest position, tension is greater, your normal reaction force is also greater. Why? Normal reaction force is mv square by r plus mg, right? This is why normal reaction force at the lowest position is greater. And that is going to be it for circular motion. See you in the next section. The next topic we're going to talk about is gravitational field. And the first thing we will talk about is law of gravitation. So what is the definition of gravitational field? It is a region of space where a mass experiences a force due to the gravitational attraction of another mass. So let's say there's you, our mass, and there's a massive mass, Earth. Let's consider both of you to be in an isolated system. In this case, what's going to happen? You are going to exert a force X on Earth, that is attracting towards yourself. And the Earth will also exert a force X towards itself, that is attracting you towards its center. So both of you guys are exerting the same amount of force X. Why? That is due to your Newton's action and reaction force, right? Same amount of force, direction is different. That's the only thing, right? So how do we get to that? I mean, the specific formula of what amount of force is exerted, we're going to learn about that. But before that, I'm going to give you a short heads up. That is, in case of electric fields, what happens is electric fields, there are both positive and negative charges, right? There are both positive and negative charges, which is why there is attraction and also repulsion. Meaning, in case of positive charges coming together, there is repulsion, right? There is repulsion. Hence, electric fields are outwards. In case of a negative charge and a positive charge, if they come together, there is attraction. There is what? Attraction, which is why fields are inwards, attractive forces. Now, in our case, gravitational field, the forces are always attractive, meaning Earth pulls you towards itself and you pull Earth towards yourself. However, the Earth is not going to move towards you because it's such a massive mass, but you're going to go near the Earth's surface because in comparison, you're a very small mass. So for the same amount of force, it is, able to do work on you, but not much on Earth. Fair enough. Now, in case of gravitational field, what do we see? Let's say you keep a box at any height, if you leave it, it is going to fall down because weight is acting on the box, right? And that weight is acting due to gravitational field. Fair enough. So gravitational field can only attract and never repel. Now, important part is this, Newton's law of gravitation. This is where we understand the formula. So what was experimentally determined is this proportionality, that is, force is directly proportional to the product of the two masses divided by their separation squared. That is, if I have two masses over here, the force exerted by this mass on this mass or this mass on this mass is going to be exactly the same. How do we find out that mass? We're going to find the product of both the mass divided by their separation from the center of both mass, and we're going to get a proportionality as such this. So force is directly proportional to the product of both masses and inversely proportional to the square of separation. So again, if I define the law, it's going to be the gravitational force between two point masses is proportional to the product of the masses and inversely proportional to the square of their separation, right? Fair enough. Now, in this case, M1 larger, M2 smaller. Both forces are Newton's action-reaction pair. No repulsion, only attraction takes place over here. So same amount of force exerted on M, same amount of force exerted on M2. Fair enough. Okay. Now, if I want to remove this proportionality sign, what I get is the main formula. That is going to be F is equals to G times M1 times M2 divided by your distance or separation squared. Now, this gravitational constant, again, experimentally found out. And so this is going to be your formula. And the gravitational constant is going to be given in the data booklet. Fair enough. So this is how you find the force between any two isolated masses, right? Now, what are point masses? In the definition, you noticed I mentioned 2 point masses. Point masses are basically when you can consider all of the mass to be concentrated at a single point, such that you can calculate the distance. Now, let's say you have this massive mass. Where are you going to consider the distance from? From the surface, from the other surface end, from the middle, from somewhere else inside? Where? Exactly at the center where the mass is thought to be concentrated in. What does that mean? Let's say I have this uniform spherical mass. I can say over here that since there is attractive forces, these are the field lines. Notice the field lines are always perpendicular or normal to the surface. If I draw a tangent over here, it is always normal to the surface. Hence, it is always radial. The field lines are always radial. It is never going to be like this. It is never going to be like that. It is always going to be radial. Notice, if I draw multiple lines over here, notice all of these tend to meet exactly at the center. What does this tell? This tells you that I can consider the mass to be concentrated exactly at this center. This is your point where all the mass is thought to be concentrated, right? Center of mass, you can often call it. And this is why we consider point masses. The mass is uniformly distributed. Then we can consider this point mass approximation to be exactly at the center. Now, in case of non-uniform objects, but perfectly spherical objects, now in those cases where the mass is unevenly distributed throughout the perfect sphere, let's say in case of Earth is not a perfect sphere, but we can still make this point mass approximation. Why? You can only do that when you're calculating for large distances, because that error, you probably studied about error in AS, and you also need to know it about in P5 for physics. So that error is actually comparatively very small compared to your large distance. You will often get questions in your paper stating that why can I only make this point mass approximation for large distances? That is because the error compared to the distance is so massively different that error is not going to matter in your final answer, right? Because error very small compared to the distance for which you're calculating, right? So in case of gravitational field, you have calculations for planets, stars, and all that, which is why distance is very large, which is why this point mass approximation, even for non-uniform masses, is somewhat accurate. It's not accurate, but it's feasible. Fair enough. Now, fair enough, you don't need to know all that. Now, topic 2, circular orbits in gravitational field. This very important. Calculations come from this topic. You have, let's say, massive mass M, right? Massive mass M, you have M2. Let's consider it to be satellite. Satellite is moving around what? Earth. Satellite is moving around Earth. Fair enough. This attractive force between the two. Remember our previous topic, circular motion. This is where circular motion applies. So M2 faces a force Fg towards the center of M1. Fair enough. And M1 will also have a force towards the center of M, right? Fair enough. Now, in this case, I know that the satellite or any planet is orbiting around Earth, right? Let's consider that the satellite is orbiting exactly around Earth. Now, where is the centripetal force coming from? Where is the centripetal force coming from, right? That is the question. So, you know, in circular motion, for anything to be in constant circular motion, it needs a centripetal force. In this case, that centripetal force is provided by your gravitational force. Notice Fg towards the center of M2, again Fg towards the center of M1. This Fg, gravitational force, is providing the centripetal force. Remember the formula of centripetal force. F is equals to mv square by r, or if you further derive, F is equals to mr omega square. These two formulas you know to be of centripetal force, right? Fair enough. So I can say that mr omega square, that is the centripetal force, is being provided by your gravitational force. Very, very important, right? Now, I want to get to Kepler's third law, which is why I'm using mr omega square and not mv square by r. But it's derived from this already, so it's the same thing. Fair enough. So when I cancel m and m out from the either equations, I'm going to be left with r cube. That is, I take r to this side, r cube times 2 pi by t whole square. That is, I broke down omega as 2 pi by t discussed in circular motion. So when you break that down, omega, and you have 2 pi whole square divided by time period whole square. And on the other hand, you have gm, constant. Fair enough. Now notice one thing, when you take 4 pi square to the other side, you're left with this entire expression, which is a constant. Gravitational constant, a constant. Mass of Earth, a constant. 4 pi square, obviously a constant, right? So the two variables you have is A, the separation. What? The separation, right? The separation between satellite and Earth. It can change, it can vary, right? It can change, it can vary. Fair. The other thing that can change, other thing that is a variable, is the time period. How long is the satellite taking to move around the Earth? How long is it taking? That is another variable. Radius, or not radius, but the separation is one variable. Time period is another variable, right? Both of these now, through this expression, I can say time period, the square of time period, is proportional to the cube of separation. This is your Kepler's third law. This is what? This is your Kepler's third law. Very, very important, right? You're going to need this in a lot of calculations. Fair enough. So next thing, now how to find out the required speed to be in orbit of planet. One more thing, let me add over here. This case, I'm considering the satellite to be in exact orbit of Earth, right? In exact orbit of Earth, which is why I can consider the entire of gravitational force being applied towards its centripetal force. Since it is in orbit, that is, it is in constant circular motion around Earth, there is a set amount of force being applied, and that force at any given distance is being applied by the gravitational force. Being applied what? By the gravitational force. Due to the existence of gravitational force, it can pull the mass towards itself. which is why it is able to be in that circular motion. So I'm considering it to be in what? In orbit, right? That is exactly what I'm talking about over here. Since the satellite is in orbit, it needs a certain orbital velocity. Remember, for circular motion, I found out that there is a specific velocity. There's a specific velocity for which the object can maintain the circular motion. Similarly, over here, a similar concept applies, that for the object or satellite to be in that circular orbit, it needs a set amount of velocity called orbital velocity. Without the orbital velocity, it won't be in orbit. How do I find that orbital velocity? Notice one thing. For this, I'm going to use centripetal force as mv squared divided by radius, right? Not mr omega square. I don't want to find the relation between radius and time period. I want to find the velocity. Hence, what I do is I equate mv squared divided by r, which is my centripetal force. I equate it to gmm by r square, which is what? Your gravitational force. When you do that, you cancel the m's off and you're left with v square, that is orbital velocity square, is equal to gm by r. Now, when you make v the subject and take a root on the right hand side, you're going to be left with root over gm by r. Okay. Now, if you know the gravitational constant, which you do, if you know the mass, this mass is, by the way, I didn't write it very neatly. So this is basically the mass of the Earth, right? This is not the mass of your satellite. The mass of satellite gets cancelled off over here, right? This is your mass of the Earth. So when you know the mass of Earth and you know the radius, again, the radius or separation at which the satellite is, you will find out the orbital velocity that the satellite needs to be in orbit at that position. So for different positions, that is 1 meter away from Earth, 2 meters away from Earth, 3 meters away from Earth, you need different orbital velocity to maintain orbit. To maintain what? To maintain that orbit. That is what this expression is telling you. So G and M is usually a constant. What changes is your separation. So for different separations away from Earth, different orbital velocity is required to remain in orbit. Fair enough. So that is your orbital velocity. Okay, what else? Okay, so the other thing I'll talk about is, notice for this expression of orbital velocity, that is root over gm divided by r, over here there's no mention of small mass m. What is the small mass? Mass of satellite. That means a very, very important information. That is telling you that the mass of satellite doesn't really matter. The mass of satellite does not really matter. Meaning, doesn't matter how heavy your satellite is, it is not going to change what velocity it needs to remain in orbital, in orbit. Hence, if I have a 100 kg of satellite, if I have a 10 kg of satellite, both needs the same amount of velocity at, let's say, 1 meter away from Earth. So for the satellite to be in orbit around Earth, both the 100 kg and 10 kg of satellite needs the same orbital velocity to remain in orbit around Earth. Understand that very carefully. These are very conceptual stuff that you need to understand to often answer certain trick questions. Fair enough. Next thing, how to find out the distance of satellites to maintain geostationary orbit. Okay. So, the thing over here is, I did not yet explain geostationary orbits, so I'll first do that. So, geostationary orbits, what are they? A few properties you need to remember about geostationary orbits, and these are going to be that it remains directly above the equator and about one fixed point. So let's say on this planet Earth, I choose my home to be the fixed point. So I want the satellite to be exactly above this fixed point. That is my room. And I want the satellite to orbit along with me. So as the Earth rotates, this is me on planet Earth and this is the satellite. I want the satellite to rotate with me and it should stay exactly above my head or exactly above my room, right? So that is what one property of geostationary orbits are. That is, it remains exactly above one fixed point. Other thing is, it moves from west to east in the same direction as Earth. So Earth moves from west to east because actually the logic is sun rises on the east and sets on west. Hence, the Earth has to move from the west to east such that the sun can rise on the east. Sun, this is sun. Sun rises on east, rises on east, rises on east, and sets on west. Which is why we know that the Earth is moving from the west to east. So it's going from west to east, right? Hence, the satellite, since it is remaining in geostationary orbit, being exactly above the same point, it should also move with Earth, meaning moves from west to east. Fair enough. Third point, it has an orbital period equal to Earth's rotational period, that is 24 hours. So you know, 1 day equals to 24 hours. Hence, the satellite also has to move with Earth exactly in sync, right? So the time period for satellite should also be 24 hours, right? Fair enough. So let's say a question, a satellite in geostationary orbit appears to remain above the same point on the Earth and has a period of 24 hours. Take two other features of geostationary orbit. It remains directly above the equator or has an equatorial orbit. Now, one thing I forgot to explain a bit further is that it needs to be directly above the equator. Let me explain it through the diagram. So notice one thing. This line, this pink line, is basically the equator. So the satellite needs to remain above the equator to maintain the geostationary orbit. Because notice one thing, if the satellite is over here, let's say that is a non-equatorial orbit. In this case, what happens is it is hard for the satellite to maintain the same rotation as of Earth. It is very difficult for the satellite to maintain the same rotation as Earth. Why, you ask? Because when you are at this position, your force is in this direction towards the center of Earth. Hence, you're supposed to rotate in which direction? Like this, right? Or, basically like this. So it comes over here, goes back, comes over here, goes back, right? That is how it's supposed to work because the force is towards the center. Over here, if it wants an orbit as such this, it actually needs extra bit of force to be exerted by external factors. Let's say some engine it needs, some amount of fuel it needs to maintain this sort of orbit, right? Fair enough. Now, in case of these orbits, that is equatorial orbit, it can remain exactly on top of one fixed point. The other thing is it can maintain 24 hours of orbit, and that force that is being applied is due to gravitational force between satellite and Earth, which is exactly towards the center, which is why it is able to maintain the geostationary orbit. Whereas comparing it with this sort of orbit, it is not a geostationary orbit, right? For geostationary orbit, it should be an equatorial orbit or about the equator. This again, from North Pole to South Pole, is not an equatorial orbit because it is going out of sync from the fixed point. That is, Earth is rotating in this direction and your satellite is moving in this direction, right? Right. Which is why you're not in sync with one fixed point. You're moving over multiple locations of Earth. So it is not a geostationary orbit. So yeah, for the geostationary orbit, it needs to be exactly above the equator. Fair enough. If you understand that, great. So now understand that to remain in orbit, the satellite first uses its thruster and needs to accelerate to the orbital velocity at that altitude. Then its thrusters are released the satellite remains in orbit at orbital velocity. Remember, we figured out orbital velocity, that is the velocity any object needs to remain in orbit at any given distance. So for 2 meters away, a certain orbital velocity needed. At 3 meters away, another orbital velocity needed, right? So what we understand is for different distances, different orbital velocity needed. Now, how do we reach that orbital velocity? Now, when you release an object that is far away from Earth, it is going to fall towards the center of Earth. So how do you make it orbit? So the first job is it needs to get into the orbital velocity. It needs to what? It needs to get into that orbital velocity. How? Usually thrusters are used or any sort of fuel is used to make that object or satellite reach the orbital velocity. Once the orbital velocity is reached, it can maintain the orbit around Earth, right? Okay, that's one thing. And now let's talk about how to find out the distance the satellite needs to be in to maintain geostationary orbit. Remember, one of the features of geostationary orbit, it needs to have a time period of 24 hours. That is, it needs to complete one entire circle in 24 hours. So remember the formula or proportionality, that is r cube is directly proportional to a time period square. Here I have a specific time period to meet. Hence, I need to find out at what altitude the satellite needs to be in for this 24 hour of time period to be met, which is why we're going to use Kepler's law over here. So I'm going to find out. Remember, this was the constant. I'm bringing the constant over here to get the answer. So I'm going to find the separation. I'm going to find the separation at which 24 hours of time period is met. So the satellite remains exactly above the fixed point and is rotating along with Earth in sync. So plug in 24 hours over here. That is, you need to convert 24 hours into seconds. G you know, given. Mass of Earth you know. 4 pi square, constant you know. Now when you take a cube root over here and cancel the cube over there, you're going to find the separation or altitude, not the altitude. Altitude is basically from the surface. Separation is from the center of Earth to the point of satellite. So this is actually the separation. That means from the center of Earth to the position of satellite. So yeah, the altitude will be basically separation minus radius of Earth. Anyways, this is going to give you the separation from the center of Earth to that point at which the satellite needs to be in. So this is how you find the separation at which the satellite needs to be in to maintain geostationary orbit. To maintain what? Geostationary orbit. Fair enough. So at any time period, if you want, let's say I want the time period to be 48 hours. Well, yes, it's not going to be if it's not going to be a geostationary orbit, but it will maintain 48 hours of time period if you meet or be in the exact position according to this formula. So you plug in 48 hours, transfer it to second, and plug it in over here, G, M, 4 pi square. You will find the altitude that the satellite needs to be in to maintain that time period. Fair enough. Great. Now this is extra bit of information I covered in my full course playlist. I'm not going to talk about it over here. Anyways, next important part is the concept of polar orbit. Remember, from north to south pole, there is another sort of orbit that is called polar orbit. Now, even in this case, notice one good thing is, although it is a lot of, geostationary orbit or equatorial orbit, even in this case, the force is exactly towards the center. Force is where? Exactly towards the center. Which is why it can maintain the orbit. You don't need extra bit of force to be applied over here, since the force is acting exactly towards the center. Acting where? Exactly towards the center. Now, the reason this is not used in some cases is because it doesn't remain above the fixed point. The position of the satellite with respect to Earth keeps changing. So it gets around different positions of Earth, which is why it doesn't stay above one fixed point. That is why it is in some cases not used, but it also has its own useful cases. Let's understand that. Polar orbits are orbits where the satellite rotates about the axis of both poles, that is like this. It is not geostationary, meaning it is not fixed about one position on the ground and does not have, does not move along the equator. It orbits at lower altitude. It orbits where? At lower altitudes. Fair enough. Hence, the time period is lower. Remember the Kepler's law. R cube proportional to time period square. So, if I want, in case of polar orbits, for the satellite to be at lower altitude, that also means the time period will be lower. Because lower altitude, so for it to complete one entire circle around Earth, it needs less amount of time. Great. Since the satellite is at lower altitude, information can be transmitted faster with less data loss. Remember, in case of geostationary orbit, it needs to be at a certain altitude above the Earth's surface for it to maintain that orbit. That is usually really far up compared to polar orbits. In case of polar orbits, I can definitely make sure what altitude I need or I want. And polar orbits are usually used to, let's say, cover up a great distance around Earth or gather information from different positions around Earth, right? So in this case, I can determine at what altitude I want the satellite to be. Let's say I want it to be exactly 10 meters above us. So the time period or the orbital velocity will be set according to that. We'll use the orbital velocity formula, this, and we'll also find the time period. Now notice one thing. Since the altitude is lower, right? Since the altitude is lower, the time period is going to be lower. So it is going to come back to the same position within a shorter period of time. The other thing is, since the altitude is lower, the amount of data loss is less. Usually it is known as attenuation, but you don't need to know that. Basically, when any bit of signal or information travels a large distance, there is a data loss taking place. So in geostationary orbit, transmitting information to and from the position takes a longer time because greater distance and there is greater data loss. In this case, it is happening faster and takes less amount of time. That's the benefit of polar orbit. Understand that. Great. Now the important sides of gravitational field. We're just getting started for gravitational fields. It's a large topic comparatively. Anyways, now this topic we're talking about gravitational field strength. What is gravitational field strength? GFS or gravitational field strength at a point is defined by the force per unit mass. Up till now, we understood force with respect to two masses and we found out the net force, that is gmm by r square, net force. Now we're going to learn with respect to 1 kg of mass. At any given position, what will be the force on 1 kg of mass? This is your isolated, let's say, Earth. At 1 meter away, 2 meter away, 3 meter away, 4 meters away. What is the force exerted on 1 kg of mass at every given position? That is gravitational field strength. Keep that in mind. Fair enough. So deriving gravitational field strength, you don't need to know. Just remember that gravitational field strength is given by this formula. Basically, you're plugging in this formula, force is equals to gmm by r square. You're just plugging in m as 1 kg. You're just considering the mass of the small object, or let's say Earth rotating around Sun. You're considering for 1 kg of object, that is, you're considering the Earth's mass to be 1 kg. So if mass of Earth is 1 kg, what is the force exerted on it, right? So you're just considering small m to be 1 kg and you get the formula to be gm by r square. And this is what? Gravitational field strength. This is what? Gravitational field strength. So on any 1 kg of object, the force exerted is going to be gm by r square. That is separation between that mass and the large object, and m1 is the mass of the large object and g is gravitational constant. And this is how we find out the value of gravitational acceleration, that is gravity, and this is the gravitational field strength near the surface of Earth. So for small distances above Earth, the gravitational field strength is comparatively the same because Earth is really massive. So for small distances above the Earth's surface, gravitational field strength doesn't really change, right? Fair enough. So G is 9.81. That is, it is calculated from this formula. So near the surface of Earth, 9.81. Fair enough. So what are we talking about over here? So gravitational field strength at the surface of Earth, if you want to find it out, you plug in the values G mass of Earth, and the separation in this formula, and the separation is basically going to be the radius. Basically going to be what? The radius. And when you plug in the radius, gravitational constant, mass of Earth, you get the value of G. That is 9.81. Now, fun fact, I'm not going to talk about the fun fact, not important right now. Why is G constant near the Earth's surface? Very important. These questions usually come. That is, notice one thing, Earth is massive. Again, Earth is massive, right? When you look down on a street, do you see the street curving down? No, you don't. Because the angle by which it is curved to our bare eye is negligible. Is what? Negligible. When you go out in space and then look at Earth, you're going to see the curvature of Earth. So, when you look at any street or your floor, it is relatively straight, which is why I can make this approximation. What approximation you ask? So notice, if this is your Earth and you're looking down from space, you're going to notice the fields are radial. Fields are radial, right? This is not straight. Notice the distance between the field lines are increasing as you go away from Earth. That is massive distances away from Earth. In this cases, as you move away from Earth, the fields are more separated, meaning field strength decreases. What does happen? Field strength decreases. What's going to happen? Field strength decreases. Why? Fields are far more separated now. Hence, field strength decreases. But when you are relatively at a similar position near the Earth's surface, that is small distances above Earth, let's say a few hundred meters, it is very small compared to the radius of Earth, which is why over here, the Earth seems to be a flat line. Now, when you draw field lines over here, these have equal distances for up till small separation. Let's say a few hundred meters, or even let's say 1 kilometer. Up till that point, let's say your fields are almost uniform. The fields are not separated. They are not moving away from each other. They're relatively straight for small distances, which is why field strength we consider to be 9.81 near the Earth's surface, right? Fair enough. Now, this is again important. The field strength graph with distance. That is, from the center to infinity, how is the graph going to be like? Let me explain in short. Forget about this for now. I'm going to explain it later. So basically, from the surface, that is this surface to infinity, how is it going to vary? Remember the formula, Gm by r square. What? Gm by r square. What is the formula of gravitational field strength? Gm by r square. Now notice, field strength force is proportional to 1 by r square. Now, in your Desmos or any graphical calculator, plug in the expression y is equals to 1 by x square. What will you see? A graph as such this, which is steeper than 1 by x curve, right? 1 by x square is steeper than 1 by x. 1 by x cube is steeper than 1 by x square. That's the only difference, right? So in case of gravitational field strength, the graph of field strength versus distance from Earth is going to be a 1 by x square curve from the surface. From where? The surface, not the center. From the surface, it varies as 1 by x square, right? Great. That is how your graph is going to be, right? You're going to use this usually to find what? To find the gravitational field strength at different position, right? Now, they can tell you that, let's say, at R, your gravitational field strength is 9.81. At 2r, that is twice the radius, what is the gravitational field strength going to be? Notice, this is r. So at twice r, 2r, what is the gravitational field strength going to be? Use this formula. Basically, you're going to use ratio, and ratio is your best friend in these cases. What is it going to do? Notice one thing. I can say 9.81 is the gravitational field strength for Gm, which is a constant, divided by r square, where r is 1r. R is 1r. R is 1r. So r square. Divide that by the new gravitational field strength that you want to find out, x, let's say. X. Call it x. And again, for x, that is 2r away from the center. What? 2r or 2 radius away from center is going to be Gm, which is a constant, divided by 2r whole square. Cancel gm off and cancel r square and r square off. What are you left with? You're left with x is equals to 9.81 divided by 4. So if you simplify this, you're going to get 9.81 by 4. So at 2r or 2 radius away from the center of Earth, your gravitational field strength will be 9.81 divided by 4. It's going to be what? 9.81 divided by 4. So this is how you're going to use ratios to find out how the gravitational field strength varies at different distances. They're going to ask you, very common question, they're going to ask you to draw or sketch the curve. This is how you use ratios to find out the graph. Fair enough. Now the real question is, I understand that this is the shape of 1 by x square curve. Why is there a straight line inside the Earth? The basic reason is, I'm not going to show you this derivation, I'm not going to explain it, I've already explained it in the full course. So what we understand is when we plug in density and volume formulas to the main equation, what we get is gravitational field strength inside the Earth, that is when the mass is uniformly distributed, that is even amount of mass at every position in the perfectly spherical Earth. In that case, gravitational field strength or gravity is directly proportional to radius. So you see a straight line. That is right at the center, gravitational field strength is 0. Is what? Gravitational field strength is 0. Now, notice one thing, that at this position, it is being pulled by all masses in equal amounts. Because exactly at the center, there is a lot of mass surrounding you. So you're having the same amount of force attract you. Same amount of force attract you from all position, from all given position. Right? Hence, right at the center, gravitational field strength is 0. Okay, so this is also why, if you watch this video that I had linked in the full course, in that case, you would see that exactly at the center, if you dig a hole through the center of Earth, exactly at the center, acceleration is 0. So let's say you drop an object through Earth, if you tunnel through Earth, and if you drop an object through Earth, exactly at the center, gravity is 0. Acceleration is 0. Acceleration is what? 0. Why? Because force at the center is 0, but velocity is maximal, right? You should know these formulas. That is, if you differentiate distance, you get speed. If you differentiate speed, you get acceleration. So when speed is maximum, acceleration is 0. Very simple. From mechanics or physics, you should know this. But anyways, that is not important. It's an extra bit of information. But the basic idea is, at the center, force is 0. Till the surface of Earth, the graph is proportional. That is a straight line. Now, from the surface to infinity, it is 1 by x square curve. Why? Because we saw this, right? Fair enough. That is your gravitational field strength. Okay, now important again, gravitational potential energy. What is it? Gravitational potential energy. Up till now, I mean not up till now, but till at least grade 10, you have learned about the formula mgh, which is telling you change in gravitational potential energy for small distances above Earth. This does not apply for large distances. Why? Why, you ask? Because gravity is not actually constant. Over here, you consider g to be constant. You consider g to be 9.81. But is it always 9.81? No. Consider this graph. It decreases for larger distances away from Earth's surface. Hence, this formula, this change in gravitational potential energy formula is only applicable for small distances above the surface of Earth. Otherwise, it's not applicable to find the change in gravitational potential energy. Now understand, I told you that forces are always attractive in case of gravitational fields, right? Keep that in mind. Now over here, when you have two objects, let's say A and Earth, there is some amount of force between Earth and A, right? That is attractive force. Now, if I'm pulling A away from Earth, if I am pulling A away from Earth, I am trying to work against a force. That is attractive force between A and Earth. Understand? As I pull A away from Earth, I'm working against a force that is attractive. So I have to push A to infinity. I have to do what? Push A till infinity. Okay? Keep that in mind. So I'm applying energy, transferring energy to A to go to infinity. Now, understand one thing. At infinity, the work done on any object is zero. Is what? Zero. At infinity, the work done on any object is zero because there is no force over there. There is no what? There is no force over there. So who's doing the work done over there? Nothing. There is no work done taking place at infinity. At infinity, no work done takes place, right? So over there, the value of gravitational potential energy is zero because there is no field strength over there. There is no field strength over there. So I need to transfer energy to A to go to infinity, where gravitational potential energy is zero. Is what? Zero. Now understand that from the surface of Earth to increase to zero, how is it possible? I told you that I have to overcome attractive forces to move particle A from surface of Earth to infinity. But I just realized that at infinity, the work done is zero. So how can I increase something to zero? That is only possible if near the Earth's surface, gravitational potential energy is negative. This is why gravitational potential energy near the surface is negative. This is basically a way of explaining it to simplify and explain to you. So near the Earth's surface, gravitational potential energy has to be negative. We have to express it in terms of a negative expression, such that if we do work on it, positive work on it, we can take it to infinity, where the potential energy is zero, where it is under no influence of Earth. Okay, fair enough. Because at that point, there is no force of Earth. So gravitational potential energy at infinity is zero. Fair enough. So understand that near the Earth's surface, gravitational potential energy is negative, and at infinity, it's zero. So now, the definition of gravitational potential energy, very important, is going to be asked to you very often, is the work done in bringing a mass from infinity to that point. So gravitational potential energy is basically defined as how much energy or work was done to bring an object from infinity to a defined point. So let's say I bring particle A from infinity to 2 meters away from me, to 2 meters away from Earth, let's say. So how much work will be done in that case? I have to calculate from infinity to a defined point near Earth's surface what amount of work will be done. That is, who will do the work? Not me. Earth will do the work. Attractive forces. And as it comes near the Earth's surface, negative work is done because I increased A's energy to zero at infinity. So now it is losing all its energy from infinity to Earth, to a negative value. And that negative value is the work done on it. Why negative? Because attractive forces between Earth and the object, right? So it lost its energy from infinity to that defined point. And that amount of work done from infinity to this defined point is known as gravitational potential energy. Okay? Understand that. Now, the formula for gravitational potential energy is basically minus gmm by r. Why minus? I told you. Near the Earth's surface, there's nothing called infinity exactly. It's a theory. So, the gravitational potential energy is always going to be what? Negative, right? But at infinity, it reaches zero, increases to zero. So, gravitational potential energy always what? Negative. Attractive forces. Attractive forces always negative. Gravitational potential energy. Now, the formula, if you want to see the derivation, you can. This is the derivation. I'm not going to explain this. I've explained this before. So, you can take a look at this. Basically, if I draw the graph of force on, on let's say particle A, any particle, any mass, the force exerted exactly above the surface of Earth, that is radius of Earth, is maximum. Is what? Maximum. Why? Because it's near the Earth's surface. So the fields are stronger. Fields are closer together. Fields are what? Closer together. Hence, max amount of force is exerted, or in Earth's case, 9.81. 9.81 is the gravity near Earth's surface, which is the maximum, if you remember from the gravitational field strength graph. Hence, at that point, field strength is maximum force is applied. As you move away, the force decreases, right? Decreases to 0 at infinity. Now, when you draw a force versus distance graph, what do you know about work done? Work done is force times distance. So to find out whatever work is done from infinity to r, which is a defined point near Earth's surface, you just have to integrate from infinity to that point. Let's say it is 2 meters away from me. So from infinity to r, that is 2 meters away from me. So infinity to 2 meters away from me, whatever distance it traveled, the area under the graph, if you find out by integrating between 2 points, you'll find out the work done. That is force times distance. Nothing else. Derivation you don't need to know. I just added it over here. But anyways, just understand the formula. That is gmm by r. This is how it's derived. Minus gmm by r. Gravitational potential energy formula. Very, very important. Right? This is your gravitational potential energy. The only difference between force formula and gravitational potential energy formula is, in case of gravitational potential energy, r is going to have no power. R is going to have a power of 1. In case of force, it has a power of 2. That's the only difference. And I guess that makes it easier to remember it. Right? So this is the formula, again, formula of gravitational potential energy. Moving on. What is the difference between the previous formula, mgh and gm by r, that is gravitational potential energy? So basically GPE, or change in gravitational potential energy, told you about the change in gravitational potential energy from one point to another. It didn't tell you how much gravitational potential energy any object holds. It is always telling you the change in gravitational potential energy is always telling you for region near the Earth's surface, what is the change going to be? What is the change in gravitational potential energy going to be, right? For near the Earth's surface. However, for greater distances, it cannot tell you the change in gravitational potential energy. It cannot tell you the change in gravitational potential energy. Why? Because gravity in that case is going to change from 9.81 to a lower value, much lower value, which is why this is only applicable for near the Earth's surface. And your minus gmm by r is telling you the total work done on any object from infinity to a defined point. That is minus gmm by r. This is your change in gravitational potential energy. Now, this is also derived from this equation. How? Let's look at it. Now, fair enough. So let's say I'm going to derive the gravitational potential, changing gravitational potential energy near the Earth's surface by del h. So I have an object that is h meters away or above the Earth's surface. How do I find the change in gravitational potential energy? Very simple. What is the final gravitational potential energy, or gmm by r, radius of Earth, plus h, that you moved it, h meters above the surface, minus gmm by r. So I'm basically plugging in both the formulas of gravitational potential energy at the Earth's surface and after moving h meters above. So I'm just adding h over here, right? So minus gmm by r plus h, that is final position, minus gmm by r, that is initial position. So now I'm going to find the change in gravitational potential energy. So when you solve everything, you're going to come to this expression, right? I basically did LCM over here, right? I took gmm common out of the expression, factored it, and later did LCM. And the minus r and r gets cancelled off. You're left with this expression where h is the distance traveled by the object, and in the denominator you have r plus h times r. Okay, now consider this. r plus h is approximately equal to radius. How, you ask? Notice, Earth's radius is massive. I don't know what the exact values, but it is really, really large, some few thousand kilometers, right? Now, in case of the h, that is a small distance above radius, let's say a few hundred meters even, that change of distance compared to the massive radius of Earth is very small, which is why the h is negligible compared to radius. Hence, you can say r plus h is approximately equal to radius. This is an approximation. So I can say GMM, that is GMM times h divided by r square, because I'm considering r plus h to be r as well, approximately the same. So now notice what you get is GMM h divided by r square. Now GM by r square, what do you know about GM by r square? That is your formula for gravitational field strength. So plug in G over here, you get GMH. So del U, that is change in gravitational potential energy, is given by mgh. For what? For cases where gravity is constant and h is a small distance traveled by the object. Fair enough. This is how you get your formula for mgh, right? Now gravitational potential, what is it? Same as gravitational potential energy, but again, in this case, just like gravitational field strength, you're considering it for 1 kg of mass. So for an object that is 1 kg of mass, what amount of work will be done to bring it from infinity to a defined point? So gravitational potential tells you the work done per unit mass, 1 kg of mass, in bringing the mass from infinity to a defined point. But in this case, 1 kg of mass. So in the formula for GMM by R, just plug in m as 1 kg and the formula you get is minus GM by R, right? Minus GM by R. This is your formula for gravitational potential. Now, why is gravitational potential negative? I just explained it to you that from infinity to a defined point, the object is going to lose energy. So the work done is done by the Earth, by the massive object, attractive forces, which is why negative. When you draw the curve or graph, it is going to be at infinity, gravitational potential energy is less negative, because if I'm pushing this water bottle to infinity, I am giving it energy to reach infinity, to work against the attractive force between Earth and the water bottle, right? So I'm giving it energy to reach 0 at infinity. So at infinity, it is going to connect with the x-axis, right? But we know it is asymptotic. That is, there's nothing exactly called as infinity, nor is it ever going to cut the x-axis. It is going to approach it forever. Anyways, sad life. So over here, notice that near the Earth's surface, as the gravitational field strength increases, the work done per unit mass also increases, but in the negative direction, because as you move towards the Earth or any such big isolated mass, your negative work done increases because the force is increasing, right? Negative work done, why? Because already explained, attractive forces. So it increases, but in the negative direction. That is, it loses energy. It is losing all its energy to a more negative value near the Earth's surface, right? Fair enough. So this is how your potential versus distance graph is going to look like. At it reaches infinity, it reaches 0 at infinity, and over here it gets more negative. It gets more negative as you move towards the surface of Earth, right? So this is your potential versus distance graph. You can try and type this formula in a graphical calculator and see it for yourself, right? Fair enough. Now, how to find the change in gravitational potential energy? That is, let's say between 2 point masses. I've already explained it by explaining it over here. That is final position minus initial position. You can do that manually, or you can apply a formula, and that formula is basically going to be from the same formula, that is del U, that is final position minus initial position. Plug in the expression and take G, M, M common, and what you get is 1 by R1 minus 1 by R2. Over there, we considered a small distance h. Over here, we are considering large distances. So let's say your R1 is this position 1, which is far away from Earth. Now, this object has come to R2, a new position near Earth. So final position is going to be R2, and your R1 is your initial position. So you can do it either way. You can either consider final minus initial or initial minus final. The reason I always do this expression where I consider R1 to be the larger value, that is, if the object is moving from a larger distance to a smaller distance, understand, if the object is going from a larger distance that is far away from me to coming closer to me, it has done what? It has lost energy. Understand again. Coming from 100 meters away to only 20 meters away from me, it has lost energy. Negative work has been done. Which is why I always take the bigger radius as the denominator of the first expression, such that this value is smaller than this value, because my ultimate answer will be now negative, because 1 by large minus 1 by small is going to be a negative value. So in case of the object moving closer to any other object, I consider the larger distance first and the smaller distance later. If it was the opposite, that is, it's going from R2 to R1, I would first consider the smaller distance over here and then the larger distance over here. So my ultimate value would be positive. You can use your brain and try and plug in the values accordingly, or just always subtract larger minus smaller, and at the end of the answer, based on what's happening, give the plus or minus sign. You can do either. Whatever you're comfortable with, you can do either. But this is going to be your formula. Just remember this formula where understand the formula, not remember it. GMM times 1 by distance minus 1 by distance, where both the distance describes initial position and final position. So at the end of the day, when you're writing the answer, considering is it coming close or moving away, you're going to give the positive or negative sign. You can do that, no worries. Right? So over here, I consider this R1 to be the larger distance and R2 to be the smaller distance, such that my ultimate value is going to be actually negative, right? Because it is moving closer, so negative work will be done. So there will be a loss of energy. Fair enough. You can do the same thing for gravitational potential, where you're just going to plug in m, the small m, with 1 kg. Hence you get Gm, no small m over here because m is 1 kg. Gm times 1 by R1 minus 1 by R2. This is your formula for changing gravitational potential, and this is your formula for changing gravitational potential energy, right? Fair enough. That is gravitational potential and gravitational potential energy. Last thing, astrodynamics. That is talking about escape velocity. Now, the thing is, every object that is in orbit, it is in orbit due to gravitational force keeping it in orbit. It is under the influence of another object's gravitational field. So let's say Earth is rotating around Sun. Earth is under the influence of the gravitational force provided by Sun. Now, that is also why it is in orbit. Fair enough. Now notice one thing, that how can I make Earth escape Sun's gravity? What can I do that whatever potential energy, negative potential energy Earth has, being near the Sun's surface, how can I make Earth reach infinity where it is under no influence of Sun's gravity? How can I make Earth escape Sun's gravity? I can provide it energy. I can do work on it. How can I provide that energy? I can give Earth kinetic energy. So, granted, Earth has negative potential energy because it's near Sun's surface. I can give it energy by providing kinetic energy to Earth and make it go to infinity. where its total energy at infinity will be 0. At infinity, total energy will be 0 because it's under no influence, neither of gravity nor of me, right? Because I've provided all my energy to transfer kinetic energy to the earth such that it can escape sun's gravity. So let's understand that over here. We know from the previous case, that is when finding out your orbital velocity, go back and see what it really means. So basically, v square is equal to gm by r, expression for orbital velocity. Now, I need to find out what kinetic energy Earth has right now orbiting around Sun. The energy Earth has orbiting around Sun right now. That is going to be, since Earth is in orbit, it has a certain orbital velocity. That is exactly what I'm finding out. By v is equals to root over gm by r, where g is gravitational constant, m is the mass of Sun, r is the separation from center of Sun to center of Earth. This is your orbital velocity. Now plug it in over here, and what you get is an expression for kinetic energy of Earth, that is Ke is half times mass of Earth times v square, that is gm by r. This is your expression for kinetic energy. Kinetic energy that Earth already has, right? Now, what is the gravitational potential energy of Earth? Well, I wrote the notes in terms of satellite, but I'm explaining Earth, so why not? Anyways, so the gravitational potential energy of Earth is going to be minus gmm by r at any given position. That is what we derived previously, right? Gravitational potential energy. This is the formula we get, minus gm by r. So at any given position, this expression explains its gravitational potential energy. At any given position of Earth near Earth's surface, this is your gravitational potential energy of Earth, right? Due to being near the Sun, which is negative. Now, can you notice something interesting over here? Yes, you can. Your kinetic energy is positive, but exactly the half of potential energy. Meaning, kinetic energy is half times potential energy. Meaning, you have less kinetic energy compared to your gravitational potential energy. This is exactly why Earth can never escape Sun's gravitational field, because it doesn't have enough kinetic energy. How can it escape? The gravitational potential energy is much larger compared to kinetic energy. So total energy of the satellite, Earth, is going to be kinetic energy plus potential energy. Add them up. Half gmm by r minus gmm by r. Why minus? Because potential energy is always negative. The expression you get for total energy of Earth is gmm by 2r. Hence, the total energy of Earth is negative. But to go to infinity, Earth needs to have a total energy of 0. To be out of the influence of any other object, any other gravitational field, Earth needs 0 energy. It needs to be stable. It needs to have 0 total energy. Minus half gmm by r basically means it is still under the influence of Sun. It is still under the influence of Sun, right? Its total energy is not 0. Fair enough. Now, if I draw this curve, that is kinetic energy of Earth versus distance and potential energy of Earth versus the distance, what you see is as the kinetic energy decreases, it means it is moving away from the Sun's surface. Why, you ask? Notice the formula. What is the formula for gmm by r? Sorry, I just wrote it. Yeah, Ke is half gmm by r, right? This is your formula for kinetic energy of Earth that we just derived from over here, right? So kinetic energy of Earth is half gmm by r. Fair enough. Now notice one thing: as the distance increases, kinetic energy decreases, right? So as you move away from sun, the kinetic energy decreases. Now notice the formula for PE, potential energy, GMM by R. The difference is it has a negative sign and does not a half in front of it. It does not have a half in front of it. So it has double the kinetic energy, but it is negative, and it also decreases with increasing distance. Because as distance increases, potential energy decreases. Now notice, at the end of the day, you will be left with a resultant or total amount of energy, which is minus half GMM by R. It is not zero. When would it be zero though? If your potential energy was exactly minus half GMM by R. In that case, Earth, the total energy, this is the resultant. In that case, this would be the resultant energy of Earth. A straight line on the axis. That is, it does not have any energy. Meaning, the total energy of Earth is zero. It is under the influence of nothing. Literally, it is under the influence of nothing. Right? It is stable. It will be in equilibrium. Sure, call it equilibrium. It is under the influence of no other force over there. It is not resisting anything. It is not approaching anything. Now, how do I find the escape velocity of Earth? It is basically going to be whatever energy is needed provided via transferring kinetic energy. So whatever extra energy the Earth needs, I need to provide it. I need to provide that energy in terms of kinetic energy such that the object reaches escape velocity at which the kinetic energy is exactly equal to your gravitational potential energy. Meaning, when the total energy of the object is zero, Earth has escaped. So I can say your change in kinetic energy, that is from near the sun to infinity, should be equal to the change in gravitational potential energy. From, let's say, this is your sun, this is where Earth is, this is infinity. From here to here, whatever the change of kinetic energy is, it should be exactly that del Ke, change in kinetic energy, should be exactly equal to change in GPE. So whatever negative work done was done to bring the object, that is Earth, from infinity to near the Earth's surface should be met by the kinetic energy. Your kinetic energy should be exactly equal to gravitational potential energy. Right? Your Ke should be equal to your gravitational potential energy. Hence, half mv square should be exactly equal to GMM by R. The negative sign basically got cancelled over here because at infinity, your gravitational potential energy is 0 minus your initial position where it is minus GMM by R. Right? So, you have half mv square is equals to GMM by R. So now, finding the orbital velocity, cancel the m, make v square the subject, 2gm by r, make escape velocity the subject, and you get v is equals to root over 2g by r. This is your escape velocity. The velocity Earth needs to escape the influence of sun. Now notice one thing. The orbital velocity is always smaller than escape velocity. The orbital velocity is basically going to be root over gm by r as found initially. This. So, since the orbital velocity of Earth is actually lower than the escape velocity, you will never be able to escape sun's gravity because the total energy is always going to be negative half GMM by R. Right? This is why you can never escape Earth's gravity. Now the minimum Ke you can say has to be Ke is GMM by R, which is exactly equal to gravitational potential energy. So in that case, if you add Ke plus potential energy, it is going to be 0, because GMM by R, kinetic energy plus your gravitational potential energy, which is negative. If you add both, total energy is 0. Cancels off. So this is the kinetic energy that Earth needs to escape sun's gravity or sun's field. And this is the escape velocity that Earth needs to escape. So that is your astrodynamics. And that is it for gravitational fields. And see you in the next section. In this section, we're going to learn about temperature. Right? The first thing we talk about is basically types of thermometer that there are. And the first definition is of temperature. So what is temperature? How do you define it? It is going to be, is described as the measure of average kinetic energy of the particles making up the substance that is being examined. So any substance that you have, the measure of the particle's kinetic energy is its temperature. So if the particles have greater amount of kinetic energy, that means the temperature of the entire substance is greater. So if the kinetic energy of individual particles are greater temperature is seen. Fair enough. What is heat? Heat is a form of energy that is transferred between two bodies. As heat increases, temperature increases. So as you transfer more energy, temperature increases. Now, first type of thermometer we're going to look at is liquid in glass thermometer. We're very used to these type of thermometers. That is, mercury filled thermometers. So the thermometric property is the volume or the length by which the mercury increases. So basically what happens is when you heat it up, or let's say you have a fever, so due to the heat, the mercury is going to expand. So the thermometric property is telling you that based on what property of the element am I judging the temperature. So I'm judging the volume change. I'm judging the change in volume of mercury to understand what the hike or increasing temperature is. So, or otherwise you can also call it length, but basically the change in volume. Fair enough. Now the material or substance used is mercury. Now the final reading is taken from when thermal equilibrium has been achieved. In this case, between the bulb and the object or place being measured. So let's say you're measuring your own temperature. Now, what does thermal equilibrium mean? Basically, when two objects in physical contact no longer have a net exchange of heat energy while both have equal temperature. What it basically means is when the temperature of your body and of the thermometer's bulb, that is, which contains the mercury, if the temperature of both is the same, thermal equilibrium has been achieved. What has happened? Thermal equilibrium has been achieved. So your own temperature and the temperature of the bulb of the thermometer is going to be exactly the same. Hence, thermal equilibrium will have been achieved, right? Temperature is same. Great. So when the temperature is same, the whatever rise you see in the volume of mercury is going to tell you the temperature of my body or your body. So that is how thermometers work. So when the same temperature achieved, no net change of heat energy is transferred. So let's say if you have a really cold or really warm cup of tea, let's say, or you have a really warm cup of tea, it is going to radiate heat or transfer heat to the surrounding until the temperature of surrounding and of the cup is exactly the same. That is why heat is emitted. Next, now how are these thermometers calibrated? These are based on properties of the liquid, of water. So basically, freezing point of water is 0 degrees Celsius. So you take a measurement of, ice temperature or the increase in mercury, increase in volume of mercury when placed in ice, that you're going to mark as 0 degree. And you see the increase in increase in volume of the mercury when you place it in boiling water, that is 100 degrees of Celsius. So in both cases, you mark the volume and then you linearly divide the units. So from 0 to 100 divisions now. So you now know the unit change in temperature in terms of Celsius. So that is how you calibrate the thermometer. You use fixed point, that is ice point, and boiling point. Great. That is how you find units calibrated on the thermometer. So yeah, this is how you do it. Not important now, but benefits of thermometer and demerits of thermometer is somewhat important. So benefits is mercury expands uniformly with temperature. So the expansion of mercury is uniform, meaning one going from 0 degree to 1 degree Celsius, it is going to expand the same as going from 80 degrees Celsius to 81 degrees Celsius. If the change in temperature is 1 degree Celsius, the increase will be the same. So uniform expansion. Another thing is reading can be taken from the scale instantly, right? You can just look at the rise and say, oh, this is your temperature. Fair enough. In case of demerits, the range of temperature reading is less because you can, most cases, measure from a certain temperature in degrees Celsius, let's say 0 degrees Celsius to let's say 100, 105, 110 degrees Celsius. So the range is usually less. Now, what is thermal energy? Thermal energy is defined by the energy of a substance due to its temperature. Thermal energy transfers from a region of higher temperature to a region of lower temperature. So thermal energy, basically it's a measure of how hot or how cold anything is. So it is due to the temperature of any object. So if you have any cup that is, let's say, 80 degrees Celsius, it has greater amount of thermal energy because it has a greater amount of heat. If you have something that is 20 degrees Celsius, it has less thermal energy. So whatever energy it has, it is going to be less compared to the warmer object, right? Fair enough. Second type of thermometer is going to be volume of gas thermometer. So over here, the thermometric property is the pressure of gas due to increase in temperature. Over here, you're going to apply Charles' law, which is saying volume is proportional to your temperature. What is happening over here? So when you increase the temperature, the gas will want to expand. Why? You're transferring energy. The gas particles are going to have a greater amount of kinetic energy. So it applies a greater amount of force on the walls of the container or whatever you have over here. So it exerts a greater amount of force on the surface. So it adds pressure. It increases the pressure. To compensate for the increased pressure, it is going to expand, right? To compensate for the increased pressure, it is going to expand. Hence, volume is proportional to temperature, right? So as the temperature increases, gas expands, pressure increases, and causes the mercury to be displaced by height h. There is a bit of mercury over here. So whenever you have increased amount of heat, there is going to be pressure exerted over here, which is why this mercury over here is going to now increase in height, because there is probably something like this we have learned in O levels, if I'm not wrong, where you have YouTube, and you have to calculate the change in height to calculate how much pressure has been added, right? So similar to that logic over here, whenever the pressure increases, that is, heat is applied to the gas, since it expands, it exerts a pressure over here, which is why your mercury is displaced by a height. And now using the change in height, you can calculate what amount of pressure has been exerted. Hence, what was the change in temperature? What amount of temperature has been changed, right? So volume is proportional to temperature. We can apply that formula. Fair enough. So, I mean, these are not questions that explicitly come in your paper, but anyways, types of thermometer you in general need to know as per the syllabus. Anyways, benefits of thermometer. It can measure a wide range of temperatures. Fair enough. Demerits of this thermometer: readings read need to be calculated and taken from graph. Meaning you have to first draw a graph to identify that what increase in pressure or what increase in volume is going to dictate my temperature. So you need to first draw a graph, and whatever, let's say, your pressure changes or volume changes, you need to then identify what the possible temperature is by drawing a line on the graph, taking the reading from the graph, or by calculating using the straight line equation. So either you can do. So basically, the demerit is it is a lengthier process, and benefit is wide range of temperature can be taken. Other one is resistance thermometer, where the thermometric property is the resistance of wire. As your temperature rises, your resistance also increases. So by measuring your resistance, you can have an idea of what the what the temperature is going to be. So benefit has a high range, and demerit is there is no direct reading. You need to calculate the resistance and then figure out the temperature. Okay. So so the substance over here used is the wire. The resistance, change in resistance, and how much it's going to change is going to depend on the type of wire, by the way. Anyways, fourth type of thermometer is thermocouple thermometer. I mean, all of these thermometers, you just need a basic small idea that such that if they ask you what is the benefit or demerit of using this, you will know what to write. Fair enough. Thermocouple thermometer is going to be the thermometric property over here is the potential difference or EMF across two wires. So let's say thermocouples you know from O levels most likely. So there's going to be two junction over here, and these are going to be made using two different kind of wire. So when you put those in two different places, you're going to find a potential difference between both places, and using that you can find out the temperature of one point. So let's say this point or this junction you're using to find temperature of any position of, let's say this junction is being used to find the temperature of this cup, let's say, right? And the other one is going to be in a fixed condition, be it heat of known temperature, be it a cold temperature of known temperature. Over here there needs to be a known temperature such that I can find the potential difference between my cup and that known temperature, right? That potential difference will let me know that what is the temperature of this junction or of this cup, right? So due to that change in or difference in temperature, I will find out the potential difference, right? Which is why I can find the temperature at the end of the day. Fair enough. This is from the book, Difference Between Resistance Thermometer and Thermocouple Thermometer. Robustness, very robust, less robust. I don't know. This is kind of weird. Anyways, it was mentioned in the book. That's why I'm showing it over here. But there's a bunch of features. You can look at the possible benefits and demerits of using either thermometer. I've never really seen these come in question papers, so I'm not focusing much on them. Next is temperature scale. There are two types. Celsius scale, of course. Celsius is when these are based off of melting point and your boiling point of water. So 0 degrees, as mentioned, freezing point, 100 degrees, boiling point. So this scale had been figured out based on the property of water, right? Okay. This is going to vary with changing pressure. That is, let's say you change the pressure you change the pressure. Let's say your atmospheric pressure changes. The temperature in terms of Celsius at which your water is going to boil is going to change. So if you decrease the pressure acting on the surface of water, it will be easier to evaporate your water. So your boiling point decreases, right? So that is basically how Celsius scale works, that it is based on the property of one known substance, that was water, and based on that we created a temperature scale. Now Kelvin scale is an absolute scale, absolute temperature scale. It is a thermodynamic scale and does not depend on the properties of any substance like that of Celsius scale. Temperature is a measure of kinetic energy, and Kelvin scale takes that into account, which is why we use this into the formula. So in the thermodynamic, in terms of thermodynamic temperature, 0 degree, so not 0 degree, I mean 0 Kelvin is absolute zero, meaning no bit of kinetic energy exists at absolute zero, which is why temperature is zero. Again, temperature is a measure of kinetic energy of any substance. So if the kinetic energy is zero, that means your temperature is zero. Whereas in Celsius scale, what you had understood is at zero, you get ice, right? But having ice, 0 degrees Celsius doesn't really mean that's the lowest temperature, right? In case of Celsius, what you see is temperatures go to negative values. But in case of the thermodynamic scale, the lowest value is zero. There is no negative value because the lowest amount of energy you can possibly have is zero. There is nothing called negative energy, right? Negative thermal energy, which is why absolute zero or zero Kelvin is the temperature at which there is no internal energy, right? There is no internal energy since there is no kinetic energy of the object. And you know that temperature is a measure of kinetic energy. So if temperature is zero, that is 0 Kelvin, at that point, everything is, nothing is going to move. Everything is going to stop, right? So at that point, internal energy is considered to be zero. And we are going to understand later on when talking about thermodynamics, I guess, that why internal energy is zero when there is no kinetic energy. We're going to talk about that later on in, I guess, ideal gas or thermodynamics. Fair enough. So at absolute zero or 0 Kelvin, there is no internal energy. Keep that in mind. All molecules have zero kinetic energy and zero potential energy. There is no attraction between the particles at that point. So converting Kelvin to Celsius, 0 Kelvin, you can say is minus 273.15 Celsius, and 0 degrees Celsius is positive 273.15 Kelvin. Fair enough. So converting, let's say, 15 degrees of Celsius, you're going to do what? You're going to say 15 degrees Celsius is going to be 15 plus 273. 15 plus 273.15. Whatever this is 15 degrees Celsius in terms of Kelvin. Great. Now, triple point you don't need to know. Never comes. Now, energy with changing states. Very important. Kinetic energy in particles. Ke of particles increase as temperature increases. They start vibrating more. So as you increase temperature, obviously its kinetic energy increases because temperature's definition, try to remember, temperature is basically the measure of kinetic energy of any substance, right? In terms of its particles kinetic energy. So if there's a warm substance, the particles of that substance must have a greater amount of kinetic energy. Now, potential energy in particles, potential energy of particles depend on distance between themselves. The electric potential energy increases to zero at infinity. Electric potential energy? The potential energy increases to zero at infinity. Basically, as you know from gravitational potential energy, gravitational fields, the previous topic, I guess, notice as separation increases, the energy increases to zero. Try to remember that as you move further away from another object, the energy of the object at infinity increases to zero. And when it is close, where two particles are close, there is greater amount of attractive force. Hence, its energy is negative. Its potential energy is negative. So as it moves away, further away, its potential energy does what? Increases. Right? As separation increases, potential energy increases. Fair enough. So when particles are close together, attraction is large, but your potential energy is negative. Hence, if separation increases, potential energy increases since it reaches zero. Now, with different states and its kinetic and potential energy. Intermolecular force, you already know. Solid has strongest, liquid has slightly worse, and gas weakest or negligible. Now, in case of solid, kinetic energy is the least because they're not moving. In liquid, a bit higher. In gases, max. Potential energy in solid is most negative. Why? Because they have a lattice structure and they're closest together. In liquid, it is slightly higher, meaning it is reaching zero. meaning they can move away, slightly away from each other. They're gliding over each other. In gases, maximum potential energy is seen. What is seen? Maximum potential energy. Because everything is moving far apart from each other. There is great distance between each particle. At least compared to their size, the distance they cover is massive, which is why it is thought that their potential energy is zero or negligible. That is the topic of ideal gases. In ideal gases, we consider potential energy between two particles, gaseous particles, to be zero because they're this small. However, the distance they cover is massive. So the distance between both the particles or any two isolated particles are very large, which is why they are considered to have almost zero potential energy, hence maximum potential energy. Now with temperature, how does potential and kinetic energy change? So let's say from AB, that is increase in temperature, so you're heating up, and again C to D, that is it is in liquid state, and A to B solid state, and E to F gaseous state. So whenever your temperature is increasing, what happens? Kinetic energy increases because temperature is increasing. But potential energy does not change. Why, you ask? Because the distance covered is not going to be changing. Because when the object is still a solid and has not changed state, they're still in the lattice structure. The distance between them is still almost the same, which is why your potential energy does not change in increase of temperature. However, from BC to DE, when state change occurs, what happens is kinetic energy stays the same because temperature is not increasing, because state change happens at the same temperature. Let's say boiling point or freezing point. So state change happens at the same temperature, and that state change, solid turns to liquid, liquid turns to gas. Hence, due to that state change, the distance between the particles now substantially increase, which is why you see change in potential energy. So from solid to liquid, let's say, it is going to have a greater distance between the particles, right? So potential energy increases. From liquid to gas, greater distance covered, which is why potential energy increases even more. And notice one thing, over here, your time required for this state change is greater. Why, you ask? Compared to B to C, the reason is from D to E, the change is greater. Greater amount of potential energy is increased. Understand? Greater amount of potential energy is increased. Why? From liquid to gas, it is actually breaking all intermolecular forces and getting into gaseous state. Whereas from solid to liquid, the change is not as much. Sure, it is turning into liquid, but it is still, can be contained in a container, right? It is not going to break free from each other. From liquid to gas, the change is massive. The distance is going to massively increase between one particle to another, which is why from D to E, the distance covered on the graph in terms of time is greater. So greater amount of time is required for the transfer from D to E, that is boiling, right? Great. Now, specific latent heat of vaporization is higher than specific latent heat of fusion. That is, vaporization means boiling, fusion means from solid to liquid. So, since for vaporization, the bonds are completely broken, and for fusion, it is partially broken, your change in potential energy in case of latent heat of vaporization is greater, right? So your latent heat of vaporization is greater than latent heat of fusion. The next thing is, for vaporization, energy is also required to overcome the pressure to change to gas. So it has to break that surface, right? It has to break that surface and convert to gas, which is why it requires a greater amount of time. Also, it requires greater amount of energy. Now, last thing, semi-last thing, now cooling effect due to vaporization. Molecules with most energy speed will escape the liquid surface as gas. So you know about evaporation already, that let's say on the surface, whichever molecules have the greatest amount of energy, they're going to leave the structure. So they're also leaving with the greatest amount of energy. So they're taking energy from the rest of the liquid and leaving the family, meaning the rest of the liquid is now going to be cooler, meaning they're going to have a lower temperature because a lot of the energy the particles have taken and left, right? Which is why there's a cooling effect when evaporation takes place. Molecule with max kinetic energy leaves, decreasing the average kinetic energy of the liquid now, which is why temperature falls. Fair enough. Heat capacity and latent heat. So heat capacity is del Q, your energy transferred is del Q. M is the mass to which the heat has been transferred times specific heat capacity times del theta. So what did I write? Del theta, or change in temperature, whatever you want to say. This is your formula for energy transfer to anything. M is the mass to which it has been transferred. C is a specific heat capacity, and del T is a temperature by which the temperature of mass increase, basically. Fair enough. So that is your formula. You already know it very well. And with low specific heat capacity, the objects heat up and cools down faster. So whenever you have anything with a lower specific heat capacity, that means you need to transfer less amount of heat. So if your C is less, del Q will be less. So less amount of heat needs to be transferred for the temperature to rise. To do what? For the temperature to rise. Fair enough. Great. So high specific heat capacity, the object heats up and cools down slower because you need to transfer greater amount of energy for the same increase in temperature. Now the next thing is latent heat capacity. That is the energy required to change the state of 1 kg of substance without any temperature change. Now basically there are two types of latent heat capacity, that is changing from solid to liquid or liquid to gas. So basically it's a state change where temperature is not increasing but the state is changing. So you're adding energy, giving energy to break the bonds. To do what? Break the bonds. So latent heat of fusion is energy required to change 1 kg of solid to liquid without any temperature change. Latent heat of vaporization, energy required to change 1 kg of liquid to gas without any temperature change, right? Fair enough. Now, this is the energy transferred. This is your latent heat capacity. And this is your mass. So, by this formula, you can find out how much energy needs to be provided for the state change of any substance, of any mass, right? Fair enough. So, that is your temperature, in short. Next, I guess, ideal gas or thermodynamics, something, right? Fair enough. See you in the next section. In this section, we are going to talk about ideal gases. So first up, laws of ideal gases, that is Boyle's law, Charles' law, and pressure law. Now, the first one is Boyle's law. What does it say? If your temperature is constant, that is, temperature is constant, pressure is inversely proportional to volume. Let's say you know this formula that your thermodynamic temperature is proportional to the product of pressure and volume, right? If you know this, you can say if temperature is a constant, pressure is inversely proportional to T by V. And if temperature is constant, I can omit it and say pressure is inversely proportional to volume. Now, think of it theoretically. If you have any mole of gas in a container, if you press down on the piston and decrease the volume, pressure increases. So decrease in volume, increase in pressure. So inversely proportional. Great. Now, as the temperature does not change, the kinetic energy of the particle stays the same as well. However, if volume decreases, the number of collision per second increases. If kinetic energy is constant, the velocity is constant as well. Now, what's happening is when you're closing down the piston or decreasing the volume, you're making the particles, the gaseous particles, collide with the plate or piston or the container far more due to a reduced space. The particles can only go to a select few places now, right? Initially, the space was greater. Now, the space is much less, which is why it can't travel a larger amount of space, which is why greater amount of collisions will be seen. However, kinetic energy is actually constant because temperature has not changed. And since temperature has not changed, kinetic energy has not changed either, right? Because temperature is a measure of kinetic energy. If temperature is constant, kinetic energy is also constant. Now, for each collision, what do you know the force exerted to be? If you remember from AS, mv, that is final v, minus mu, initial velocity, divided by time of collision, you're going to now get the force exerted by each particle. This is the force exerted by each particle. The velocity with which it rebounds, the velocity with which it hits the container face. This is the time of contact. And this is the force that is exerted by one particle. Now, N is the number of collision. Now, one particle is obviously not going to collide with your container. There are multiple particles, and to consider that, we say N particles. Now, since number of collisions increase, that is, number of times the particles are going to collide with your wall increases, the force applied over an area also increases, right? So, as you decrease down the volume, this is why your pressure increases, because number of collision has increased. Fair enough. So, I can say that P1V1 is equals to P2V2. Why can I say that? Because considering temperature to be constant, I can say P is proportional to V. Sorry, P is proportional to inverse of V. Hence, I can say, if this is the constant, I can say that P times V is proportional to 1, right? P times V is proportional to 1. And the moment I remove this proportionality, I can say P into V is equals to T, right? Granted, the temperature is constant. I can have a different pair of volume and pressure as well, right? T is equals to P2 V2. What do I mean by that? Let's say in one case, I have 10 as my pressure, and let's say I have 2 as my volume, 2 meter cube, right? This is going to give me 20, right? This is going to give me 20. The other case is, let's say I have my pressure as 2 and my volume as 10, and this is also giving me 20. So, as long as the product of pressure and volume is the same, as long as the product of pressure and volume is same, your temperature will be the same. What? Your temperature will be the same if your product of pressure and volume is same, right? So now, when you draw a graph between P and inverse of V, it's going to be a straight line. However, if you draw a graph of P and V, it's going to be a 1 by x curve, right? A typical 1 by x curve. Fair enough. Because P is proportional to 1 by V, right? The other thing I'll add over here is the area under the graph. Notice, the area under the graph is going to give you P times V. And remember from AS that work done is pressure times change in volume, right? If your pressure is constant, if you know the change in volume, if you find the product, you get the work done on the gas or by the gas. Similarly, over here, when you find the area under the graph, you're finding P times V, P times change in V. Over here, the issue is pressure is not constant, which is why you need to integrate from V1 to V2. I mean, in this syllabus, you don't need to, but I'm just saying that the area under this graph is supposed to give you the work done on the gas or by the gas, right? The work done on or by the gas. So this area is work done. Fair enough. Next up, Charles' law. What does Charles' law say? If the pressure is constant, volume is proportional to temperature, right? If your thermodynamic temperature is proportional to product of volume and pressure, if your pressure is supposed to be constant, that is cancel it off, temperature is directly proportional to volume. That is, let's say you have a container, piston. If you heat the container, what's going to happen? Piston will move up. Why? To keep the pressure constant. Keep the pressure constant, the piston has to move up such that the volume is increased. Why is that important? Let's see. As temperature increases, your kinetic energy increases. So velocity of particles increase. Remember our force formula, mv minus mu divided by time of creation. So since velocity is increasing, change in momentum is increasing. Change in momentum is increasing. Hence, greater amount of force is being applied. So pressure is increasing because pressure is force by area. So if force increases, pressure also increases, but we want the pressure to be constant, which is why we decrease something else. We decrease the number of collision. Remember from this formula, N, we are going to decrease your number of collision. How? By increasing the volume. By increasing the volume. If I increase the volume, right, the amount of space available to the particles increase. So the number of collision between the walls and the particles decrease. So there's a decrease over here, there's an increase over here. Net, the pressure remains constant, right? Net, the pressure remains constant. Fair enough. I can also say over here that since T is proportional to V, at any point, if you increase the temperature, let's say to T2, it is also going to be proportional to V2, right? Because by whatever amount you increase the temperature, by the same proportion, volume will also increase, right? So I can say V1 is equals to V2 and T1 is equals to T2. So proportion between V1 and T1 is exactly equal to the proportion between V2 and T2, right? Fair enough. So a small example could be 1 by 2 is equals to 2 by 4. The proportion is exactly the same, right? Fair enough. Now, the graphs of Charles law, the graph of volume and temperature is going to be a linear line that is passing through origin because T is directly proportional to volume. The other thing is going to be your graph between pressure and volume. So what we're saying over here is if the pressure is constant, your temperature is directly proportional to volume. So let's say in the pressure and volume graph or curve, how is it going to look? If I vary the temperature, right? Now, if I vary the temperature, you get two separate graphs. So let's say this is 900 Kelvin. This is the graph for 900 Kelvin and this is the graph for 400 Kelvin. At 900 Kelvin, notice one thing. For the same amount of pressure, your volume is greater. Your volume is greater, right? So, due to an increased temperature, your volume is greater. At the same temperature. At the same pressure. Now, for the lower temperature that is 400 Kelvin, at the same pressure, your volume is lower. Hence, proven that your temperature is directly proportional to volume, granted your pressure remains constant, right? So if I take another example as such this, right? If your pressure is constant, notice volume is much greater, right? At a higher temperature. At a lower temperature, your volume is much lower, right? So that is how you can prove, right, the proportionality. Fair enough. That is how the graphs are going to look. Now, moving on, we're going to move on to what? We're going to move on to pressure law. Pressure law states that if the volume is constant, pressure is directly proportional to temperature. So again, temperature is proportional to P times V, right? Over here, if you increase, let's say, the temperature, your pressure should also increase, granted volume is constant. So if you have the same amount of gas in a container, let's say, if you heat the gas, what's going to happen? Greater amount of pressure builds up inside. Why, you ask? Because notice one thing, as temperature increases, kinetic energy increases. Hence, the velocity of each particle increases, meaning the change of momentum at every collision increases. Hence, force applied on the wall increases, which is why P is equals to F by A, meaning pressure is force by area, meaning pressure also increases, right? P is force by area. If force increases, pressure also increases. This is why your pressure increases. Now, I can say similarly like that of volume, T1 by, or let's say P1 by T1 is exactly equal to the ratio of new pressure divided by new temperature. The ratio will remain same. Fair enough. Now, the pressure versus temperature will look something like this, a straight line through origin. However, for, again, another case where you have two different temperature, but in a pressure and volume curve for, let's say, a higher temperature. Let's consider T2 over here. Notice for the same pressure, your volume is greater. However, I'm not judging the change in volume. I want to keep the volume constant. So let's analyze with respect to constant volume, not constant pressure. So for the same volume, that is, let's say 400 cm cube, at this same volume, notice at a higher temperature T2, my pressure is what? Greater, right? Notice for T1, which is a lower temperature, my pressure is lower. Agreed? Yes, fair enough. So you can draw the graph of PV and see that for increased temperature, what happens is the graph eventually lifts up. That is, the product of pressure and volume increases. Now for the orange line, notice at any given position, the product of pressure and volume is same. Is what? Same. Similarly, for the greater temperature, the pink line, notice at any given point on the curve, on the pink curve, the product of pressure and volume remains same, right? Remains same. Fair enough. Now, since the volume isn't changing over here, there is no work done, right? Fair enough. Now, the ideal gas equation, we have to derive that. How do we derive that? We know that pressure is directly proportional to temperature, right? And pressure is inversely proportional to your volume, right? Pressure inversely proportional to volume, pressure directly proportional to temperature. Now we can say that pressure is proportional to T divided by V, joining both the equations together. Now removing the proportionality sign, we get P times V divided by T is equals to a constant, right? PV is equals to constant times temperature. Now it was figured out that this constant is actually N, number of moles, and R, the gas constant, right? This was figured out that this constant, the red one, is moles of gas, and R, that is gas constant, that is 8.31, right? So now let's say if the moles of the gas increase, what's going to happen is if you take volume to the other side, then the pressure building up would increase. And if you take pressure to the other side and keep pressure constant, then for greater amount of moles, what's going to happen? Your volume occupied will increase, right? So depending on what you keep constant, the other variables will be affected. Fair enough. So that is how we get this PV is equals to nRT formula, very important for later calculations. Now, ideal gases, the definition for ideal gases is, these are gases that obey the proportionality. PV is directly proportional to thermodynamic temperature, right? So what does this mean? This means that for ideal gases, we make a bunch of assumptions. Let's say we don't consider we don't consider that between two particles there is any sort of potential energy. We don't consider there to be any sort of force, intermolecular force. We consider their volume to be negligible compared to whatever volume they occupy. So there are a bunch of assumptions we make, which is why we can say PV, the product of pressure and volume, is directly proportional to the thermodynamic temperature. Very important. Now, next thing is moles and Avogadro's constant. So, amount of any substance is measured in moles. If you've done chemistry, you know this very well by now. But the definition of mole is, it is the amount containing as many atoms as there are for 12 gram of carbon-12 element. So what mole really is 6.02 into 10 to the power 23 particles of anything. If I want 1 mole of this cup, I'll take 6.02 into 10 to the power 23 cups. And I'll have 1 mole of the cup. So that is basically what 1 mole means. So 12 gram of carbon-12 is supposed to have 6.02 into 10 to the power 23 atoms of carbon, right? That is how this value has been derived. Okay, fair enough. Now, these are fairly simple things, but number of moles of any gas in a given volume is the same. So if you have 1 mole of oxygen, 1 mole of carbon dioxide, 1 mole of fluorine, all of them, if 1 mole is going to occupy 24 dm cube, that is 24 dm cube or 24,000 cm cube, right? In the same condition, in the same room temperature, in the same other pressure and all those conditions, under the same condition, 1 mole of any gas occupies the same volume. Fair enough. Now, one example is find the moles of 50 cm cube of chlorine. So you're going to turn this into dm cube, 0.05 divided by 24, and you're going to get the moles of chlorine, which is going to be 2.08 into 10 to the power minus 3. Okay, now finding the number of moles using Avogadro's constant. So the number of moles is going to be of, let's say, any particle. If they say there are 6 into 10 to the power 28 atoms of, let's say, carbon, and Avogadro's constant we know to be 6.02 into 10 to the power 23. Now, when you divide this, you're going to find moles of carbon that are present in any substance, right? So if you divide the number of particles available of the element by the Avogadro's constant, you get the moles of that element that is present in any reaction, in a substance, whatever, right? So Avogadro's constant is going to be, what is it? We express the mass of any atom with U, where U is the mass of a proton or neutron. So U basically means one atomic mass unit, that is one atom. What is the mass going to be? Let's say 12 is the atomic mass unit of carbon. So carbon is represented as 12U. So it has 12 times U mass. Now 1 U is expressed as 1.66 into 10 to the power minus 27 kg, right? So the mass of carbon atom is supposed to be 12 times 1.66 into 10 to the power minus 27. Now, if I ask you what is the mass of 1 mole of carbon, you're going to multiply this with 6.02 into 10 to the power 23, because 1 mole will have 6.02 into 10 to the power 23 atoms of carbon. Fair enough. Now, fair enough. We can say every atom has a mass equal to number of proton plus number of neutron times U. So carbon has a mass number of 12. So when you multiply 12 with U, you're going to get the mass of one atom of carbon. Fair enough. So yeah. Okay. So now if I want to find out how many atoms there are for 1 mole of carbon, I can say, since 1 mole of carbon, if you look at the periodic table, it has 12 gram of mass. It has what? 12 gram of mass. 1 mole of carbon is considered to have 12 gram of mass. I'm going to convert that to kg, so 0.012. And in the denominator, I'm going to divide it by the mass of one atom of carbon. What is it? 12U. 12U. That is going to be 12 times U. This is U. That is, notice 1.66 into 10 to the power minus 27. 1.66 into 10 to the power minus 27. What I get is the Avogadro's constant. Number of carbon atoms there are present in 12 gram of carbon. 12 gram of carbon is supposed to have 6.02 into 10 to the power 23 atoms of carbon, right? So you can try this and find out how many particles there are in 1 mole for other examples as well. Take any element, and whatever is mentioned in the periodic table, that is its mass number, meaning that is how much in grams it will weigh for 1 mole of the substance. So fluorine, whatever the MR is, that is what 1 mole of fluorine will weigh, right? And then you can calculate the number of particles by dividing its mass, one mole of mass, divided by its atomic mass. That is going to be its MR times U, right? Fair enough. So it's basically mr by mr times u. So this mr is in grams and this mr is going to be multiplied with u, right? You convert this grams to kg just as I did, and in the denominator, this mr represents how many atomic mass unit. Fair enough. So this is how they got to 6.02 into 10 to the power 23. Try it out yourself for other examples as well. And you'll see that you get the same value of Avogadro's constant. Mass in grams divided by mr times its atomic mass unit, that is U. So if, let's say, take another example, helium, let's say, 1 mole of helium will have 4 grams divided by 4 times U, divided by 4 times U. And you get the, Avogadro's constant. Fair enough. Now, this is not important. I've explained that. So the kinetic theory of gas, this is relatively important. Basically, there are a bunch of assumptions that we make when talking about ideal gases. And understanding these assumptions about ideal gases is very, very important. So kinetic gas theory tells you that molecules of gases act like perfect spheres, causing a completely elastic collision, meaning each gas particle is perfectly elastic when having any sort of collision with another particle or the container. So that mv minus mu, that change in velocity is supposed to be perfectly elastic, meaning if it hits the boundary with, let's say, 12 meter per second, it will rebound in the opposite direction with 12 meter per second as well, right? That is one of the assumptions. Second is volume of molecules are negligible compared to the container volume. So we know gas particles are really, really small, right? You cannot see it with your bare eyes, right? So since the particles of gases are really small and occupy, in reality, very, very less amount of space compared to the container they are in. So let's say for this same water bottle, there is a bunch of, air molecules inside, different type of gases inside. However, notice the volume they occupy is really, really large. However, the number of atoms over there, their own volume, that is volume of their entire atom, is not that high, right? It is not that large, which is why we consider the volume of molecules themselves to be negligible compared to the volume they occupy. Fair enough. Now, the time of contact while collision is negligible compared to the time in between. So let's say, same water bottle, you have a bunch of gas particles that are roaming around. That is observed by Brownian motion. So according to Brownian motion, any particle in fluid, any gaseous particle or anything in fluid is going to be in constant random motion, which is why even in this, bottle of water, even though I'm doing nothing to it, there are gas particles moving up and down, sideways and all that, right? So all of these, we consider that the time of collision between the particle and the face of container to be negligible. We consider it to be negligible. We cannot possibly calculate for how long the particles are in contact with the wall, which is why we consider the time of collision to be negligible compared to the gas particles traveling to the distances, compared to the gas particles traveling to the distances to reach the wall of container, So we consider it to be negligible, the time of collision to be negligible compared to how long it travels till it goes there. Fair enough. There are no intermolecular forces. This I've already mentioned, that we don't consider there to be any potential energy. We don't consider there to be any intermolecular forces between ideal gases. The molecules are in constant random motion. Yes, according to Brownian motion, that is what has been observed. Now, fourth part is Boltzmann constant. What is Boltzmann constant? It is basically a formula which states your gas constant divided by Avogadro's constant is going to be your Boltzmann constant. This is just, you just have to remember it, nothing else. So R divided by Avogadro's constant is your Boltzmann constant, and it will be given in your data sheet. This is the value, it will be given to you. Now remember that PV is equals to nRT. What you can do over here is, remember, number of moles is number of particles divided by Avogadro's constant. So you can plug that in over here. And what happens is you get N by A times R times thermodynamic temperature, where R divided by Na is going to be K, as according to this, as according to that. So you get a new formula, that is PV is equals to NK3. Why is this useful? This is very useful when doing calculations in the question paper, because you will be often asked to find the number of particles. Notice small n is moles and the capital N is number of particles, okay? Fair enough. So PV is equal to NKT is another formula. This is ideal gas equation. Now, deriving the kinetic gas theory equation. This is very, very important, right? Understand this very carefully. You will often be asked to write down different steps of the derivation. So understand the entire derivation over here. Not all derivations are important. A lot of those are extra. So I'm skipping a lot of the parts that are not important for you. I'll only flag post what is important, right? So just trust. Now, as gas molecules are moving in constant random motion, they hit the walls of the container and go through a change in momentum, right? Remember mv minus mvu. So they go through a change of momentum, and that creates the force. On the container. This exerts a force on the wall. That force causes pressure. Remember, pressure is F by A. Great. Now, in this derivation, we will find the equation to get the pressure, but also find other useful equations from the derivation. Great. Let's do that. We're going to start off with step 1. Consider a cube of length n on each side. L, 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 right? So this cube is going to contain a bunch of gas molecules, right? So let's consider with respect to one specific particle, that is the red particle inside. Molecules in reality take a random route around the box. However, to derive the formula, I'm going to consider the particle moving in a straight line. Notice this is a typical trajectory of a random particle, haphazard, right? It is going to go through random motion, but in straight line. Notice this particle hits that wall in a straight line. That particle then rebounds and hits this face in a straight line. So the trajectory is never curved. It is always a straight line, right? Now, I've considered the motion of the particles to be exactly a straight line. Fair enough. Now find the change in momentum. What is change in momentum going to be? Granted, the molecule has mass m and velocity c towards the right direction, towards rightward direction. So I'm taking right as positive, left as negative. So the change in momentum as it hits the right face is going to be minus mc. So I'm actually considering this direction as negative. Sorry. Okay, so minus mc because okay, no, I was considering the right thing. Sorry. Positive and negative. Rightwards is positive. Sorry. Final is going to be minus mc because after rebounding, it's going to go to the leftward direction. So from this position, it goes to the right face, and after rebound, it's going to go to the left side face, right? So coming in to the right hand side with velocity, initial velocity c, right? Initial velocity c. And the final velocity is in the opposite direction, hence the negative sign. While the mass is same, the speed is also same. The speed is also same, just the direction has changed. Consider it to be an elastic collision. So whatever velocity it had while coming in, after the collision, it's going to have the same velocity but in the opposite direction. Fair enough. So my total change in momentum is minus mc, that is final, minus mc, that is initial. And the change in momentum is minus 2 mc. Great. Oh, I had it over here. Anyways, so minus 2mc is the change in momentum of the particle. However, we are calculating the pressure on the wall. So for the wall, the del P is positive 2mc. Now, this may be a bit tricky to understand, but let me try my best. So, me hitting the wall, right? I go through a change in momentum in this direction. Now, this wall will actually go through a change in momentum in the opposite direction. How you can try and understand that is the force exerted on the ball is, so if I hit this palm, the force exerted by my palm on this hand is opposite, is let's say in the rightward direction. But the force I exerted on the wall is in the leftward direction. Is what? In the leftward direction. But the force the palm exerted on my fist is rightwards. Which is why for me, the change in momentum is minus 2mc. However, the change in momentum for the wall is positive 2mc. Because force is what? A vector. For me, the change in momentum was rightwards, minus 2mc. But for the wall, the change in momentum happened leftwards because I hit it leftwards. And the wall exerted a force rightwards. So if you get that, you should understand that for the wall, the change in momentum is positive 2mc. Now, step 3, find the time taken. The time between collision is now going to be, remember, speed is equal to d by t. So if I want to find the time, it is going to be speed divided by distance. Distance by time, yes. So it's going to be, what did I write over here? So time is going to be distance by speed, right? So to find out the time, you're going to divide the distance traveled divided by speed. So the distance traveled is from this position to this position, that is L, and from this position to this position, again L. So it's going to be, distance is 2L divided by speed. We consider the particle speed to be c. So 2L by c. Now you will ask me that what atrocity of a derivation is this? How are you considering the time of collision to be this entire path? How can I do that? Actually, it is very complicated. I tried my best when I was first learning it to understand why the time is considered to be for the entire path and not just the time of collision. I have got to a theory as to why that is done, but I'm not going to explain this over here because if I try explaining this, it is going to take a lot of time. But the basic idea is that the time of collision between the gas particle and the wall is very small. So we cannot consider that time because in that case, the time is so small that your 2mc, your change in momentum divided by time, the time is so small that force turns out to be infinity. However, that is not the case, right? That is not the case. So what in reality happens is the particle coming from this position to this position, it loses a lot of its velocity. So it is going through a change in momentum throughout the journey. It is not just going through a change in momentum with hitting the wall. It is going through a change in momentum throughout the journey. Similarly, from this position to getting back to this position, it is going through a change of momentum. So that change of momentum, what I am considering is going through the entire journey and averaging it out throughout the entire journey such that I can get a more accurate value of pressure that is being exerted. Now, the reason I consider this is in a given box, there is not going to be one single particle and it is not going to follow a straight trajectory. There are going to be multiple particles and they're going to have a haphazard movement, which is why they're going to go through a change of momentum, non-linear change of momentum, call it, throughout the entire journey. So that change of momentum of velocity, changing its direction is not happening right at the surface of the cube. So it is happening throughout the journey. You can average it out throughout the journey. That is what we do over here. In short, I have an atrocity of an explanation over here, but you don't need to understand that. Basically, you're going to consider the entire journey for finding out the time between collision. So that is going to be distance by speed. Distance by speed, that is 2L, distance divided by your speed of particle, right? So this is going to give you the time of collision. Fair enough. So now you know change in momentum 2mc, and time, that is 2L by c, right? 2mc divided by 2L by c. Now, when you simplify everything, you get the force. Change in momentum divided by your change in time. How long it took for the change of momentum to take place. That is throughout the journey. So, mc squared divided by L. That is your force. Your force is mc squared divided by L. Fair enough? Great. This is your force that we have derived up till now. Next, step 5. Find the total pressure. Find the total pressure. It is going to be force divided by area. So take any possible surface of the cube. Take any possible surface of the cube and consider the force exerted on it. It is going to be mc squared by L, which is your F, divided by area, that is L squared. L squared. So that is your what? Pressure. Force by area. So pressure by one particle is mc squared divided by L cube. Divided by what? L cube. Now, notice one thing. There is not only one single atom, right? There are multiple atoms over there. So I'm going to consider the number of atoms and say n times mc squared divided by L cube. To consider all the atoms that exist inside the container. Since n is the number of particles inside the container, all of them exert the same average pressure, right? Since I'm averaging everything out, I can consider all of the atoms to exert the same amount of force or pressure. I'm averaging it out throughout the entire amount of particles, right? I'm trying to find out the average pressure or force exerted. In reality, let me explain this again. In reality, it is not going to be constant. That pressure exerted, that force exerted on each wall is not going to be constant. It is going to be quite random, but that variation is very less. So it is not constant, but it is going to be round about the value we find out, right? Fair enough. So n is the number of particles inside the container. All of them exert the same average pressure, right? Fair enough. So I'm considering this to be your pressure by one particle, and due to the number of particles, you're going to consider n times pressure. That is the total amount of pressure. Now, you're now going to consider n times m. Instead of c square, you're going to consider mean square speed. Now, you're going to ask me, what on earth is mean square? Let me explain. So, here we are working with average speed of particles. Agreed? As mentioned, I'm averaging it out throughout all the particles. I want to find the average speed. I don't want to find out the highest speed. I don't want to find out the lowest speed. I don't want to find out the speed of one particle only. I want to find out the average speed, right? In general, what does happen when you distribute it over multiple particles? Hence, I need to consider a number of cases. That is, one of the particles inside the container may move at 10 meters per second. The other can move at 2 meters per second. The other can move at 100 meters per second. So I have to average it out. How do I do that? I'm going to consider the square of all speeds divided by the number of speeds taken. So one is 10 square, the other is 4 square, the other is, let's say, 100 square, divided by number of speeds taken, that is 3. This is my mean square speed of the gas particles, right? So A, B, C are different speeds of the particle. Now, what is the root mean square? That is, you're going to see this C inside 2 crocodiles. So we will often need to work with just the average speed and not the root mean square speed. So for that, we're going to take root over whatever value we got over here, because this is going to give you mean square value of the speed of particles inside the container. So when you take a root over this, it's going to give you root mean square speed. That is your average speed. Average what? Average speed. And this is your average squared speed, right? Fair enough. So why do we do that? So basically, when you have a bunch of particles moving around, actually it is moving in multiple directions, Sure, the magnitude of speed is the same or similar, but it is moving in different direction. So one may move in this direction, one may move in this direction, one may move towards each other. So they're going to collide, right? They're going to come in contact. So what happens is, to consider all of that, to consider vector of movement, that is their direction, I'm going to square all the values such that I can work with the magnitude of speed, not the velocity, not the vector. So I don't want to consider which direction it is moving. I don't want to consider that. I just want to work with the average speed, right? I want to work with the average speed such that my whatever mean speed I get is the real mean magnitude of speed, right? A magnitude of velocity. So you may ask me, why not just take all these value and divide by 4? Now, what happens then is, let's say one is moving leftwards, and I consider it to be a negative value. One moving rightwards, I consider it to be a positive value of velocity. Now, when you find the mean of this, -3 plus 4 minus 3, it is not going to give you the accurate value. It is not going to give you the accurate value. You have to now square all the values and divide by number of values, and then take a root of it to find the average speed. Right? So this is how your root mean square speed is found out. So you take a bunch of speeds or velocities, you take a bunch of velocities, square that, and then take a root of the average. So you take a root of the average squared velocity, such that you're just working with the magnitude of velocity, that is speed. So I care about the magnitude of velocity. Fair enough. That allows me to then find out the pressure on the container. How? Let's see. So this N is the number of gaseous atom, M is the mass of gaseous atom, and C squared is telling you the average squared velocity. Yeah, average squared velocity. So since it is squared, it doesn't matter. The direction does not really matter. Now L cube is as according to this. So N divided by L squared, right? So it became L cube. Fair enough. So this is the ultimate formula that we get into, the pressure formula. So this is now going to be broken down to consider another factor. That is, in reality, the particles are not going to move in multiple directions. The particles are not going to move in a straight line. Now, previously, what we had basically considered is all particles will have different amount of speed, which is why we found the mean speed or root mean square speed, such that I can find the average speed of all values. Now what we're doing is we're finding the average speed of all particles in one certain direction. So I'm now going to say that the average speed squared of any particle will have 3 components: x component, y component, z component. What does that mean? Now notice, any object traveling, any particle traveling, any gas traveling will not exactly travel in a straight line. The chances that it travels in an exact straight line is very low. What really happens is the particle will travel in a haphazard motion. So whatever resultant speed it has, that is in that specific direction, has 3 components: z direction, x direction, y direction, right? So all of those speeds of all particles can be broken down into 3 directions: y, z, x, right? So I'm telling you, just like Pythagoras theorem, that this h square is equals to sum of y square and x square, I can also say that the resultant speed square in any given direction is the sum of 3 component squared. That is, it's x component squared, it is it's y component squared, and it's z component squared. If you can find the sum of all components squared, that means the speed, then you find the resultant speed squared. Because just like 2D cases, even in 3D cases, the Pythagoras theorem apply, right? If you add one more dimension to it, even in that case, the Pythagoras theorem will apply, right? So whatever your resultant speed is in any given direction, if you break that direction down, let's say anything is moving in this direction, right? Is moving in this direction. It has two components in 2D. One is a y component, the other is a x component. So y component square plus x component square is going to give you your resultant component square, right? I mean resultant speed square. Now in 3D, again same thing applies, but one is in x, one is in y, the other is in z-axis, right? Just three different possible outcomes. That is, the object can hit the right-hand side face, or the face of container towards you, or the face of container above you. So three different positions it can hit, right? And the interesting thing is, the chances that it hits container face in this side, or container face in your direction, or container face in the upwards direction, x, z, y, all have same probability of being hit. Because the motion of particles are random. Are what? Random. So it doesn't have its own free will. It can hit any of the face. It can travel in any direction, x, y, z, any. Hence, the probability or the chances that it hits any of the wall is same. So I can say the component, the speed component in all of those direction is safe. Is what? Same. I can consider it to be the exact same, because when you average it out throughout the container, you will know that all faces of the container feel the same amount of force, right? All faces of the container feel the same amount of force. Therefore, chance of hitting all of those faces are exactly the same, right? It's not that any single side of the container is going to face a smaller force or a greater force. That's not going to happen. In general, when you average it out for all particles, same chances of hitting all faces, right? Keep that in mind. So now I can say that the resultant speed squared is 3 times the speed squared of any component. 3 times the speed squared in any component. So if any particle is moving in this direction, which has a component in z, x, and y axis, the value of x-axis component squared times 3 is going to give you its resultant speed squared. Why? Because its y component, x component, and z component is thought to be the same. Because when you average everything out, at least in case of a cube, you can consider it to be same, because same probability of hitting all the faces. Fair enough. So I can say the c squared or resultant speed squared is exactly equal to 3 times component in any direction squared. So this is, you can say this is cx, you can call this cy, you can call this cz, you can call it any direction, no worries, all of those are same. So, oh sorry, it's going to be this one, sorry, cx, cy, cz. So I basically made this the subject. So your component in any one direction, if you make the subject, 3 is going to go to the other side, is going to be 1 by 3 times the resultant speed, right? So the chances or the amount of speed in any specific direction, that speed squared value in any direction is going to be 1 by 3 times the resultant speed squared. Agreed? Fair enough. So this is how we can find the speed in any one direction. We know particles don't move in one direction only. So considering that, I am saying that the speed squared in one direction is going to be 1 by 3 times the resultant speed squared. So now, since I'm considering the particle to travel in a straight line as such this, I have to consider 1 by 3 times the resultant speed of particle. 1 by 3 times what? The resultant speed of particle. Fair enough. Where did it go? I don't know. So yeah, this. So in any direction, let's say x direction, its speed is going to be, speed squared value is going to be 1 by 3 times resultant speed squared. Anyways, I know it's a bit complicated to comprehend, but I'm trying to quickly finish this such that I can go to other topics as well. But anyways, the pressure now you can express as 1 by 3 times N times M times your speed, resultant speed squared, average resultant speed squared divided by L cube. L cube is volume, right? L cube is volume. So I can now write PV is equals to 1 by 3 number of particles times mass times your resultant speed squared. Notice 1 by 3 times resultant speed squared is telling you the squared speed in any specific direction x, y, z, right? Since I'm considering the value to be, the case for one specific direction as mentioned before the derivation, that is in the x direction I'm considering the particle to travel, I have to consider it to be 1 by 3 times your resultant speed. Because again, the particle will not always travel in a straight line. Average it out, it's going to be 1 by 3 times average speed squared, right? That is, in one direction, it is going to be 1 by 3 times average speed squared. Resultant average speed squared. Fair enough. Okay, so at the end of the day, you can do another step and represent this in terms of density. That is, I can say Nm to be the total mass, that is number of particles and mass of one particle, total mass divided by volume. So I get the density, mass by volume. So I can say Nm divided by V is going to be density. So I get 1 by 3 times density times resultant speed squared. This expression tells you that in any direction, what is the pressure going to be exerted? What is the pressure going to be exerted, right? In this phase, in this phase, in this phase, or in this phase. In all phase of the container, what is the pressure going to be exerted? That is why it was important to consider for one direction only. Because when calculating for pressure, remember, force by area. So you have to consider for one phase only to find the force. And then you can say, yes, in all phases of the container, the force felt or the pressure felt is exactly the same. Because I have averaged it out throughout the derivation at every given step. Right? Fair enough. Next, you're going to go through deriving the average kinetic energy. So this was your formula for your kinetic gas theory equation, that is PV is equals to R nRT. You further derived it for this formula, for the pressure formula, that is PV is equals to 1 by 3 Nm C square, right? This is the main part which you're going to use later on again. Now, for this, what we are going to talk about is finding the average kinetic energy of particles. Previously, we found out the pressure formula. Now we're going to talk about the average kinetic energy of all particles. How to do that? Notice one thing, all particles are going to have a certain kinetic energy. Granted, it is not at 0 Kelvin. At 0 Kelvin, everything is going to stop. So, granted, it's not at 0 Kelvin. It's going to have two types of kinetic energy. One is translational, that is moving from one point to another. The other is rotational. Rotational means it usually needs to be diatomic to rotate about an axis. Not exactly important, but basically two types of kinetic energy. Now, this kinetic energy can be derived from the two ideal gas equation. One is PV is equals to NKT, that is 1. And the other is PV is equals to 1 by 3 times Nm times average speed squared, resultant average speed squared. So this is your formula that we derived previously. Exactly before this. So now when you equate PV is equals to PV, both equations, you're going to cancel a bunch of things off. There is number of particles. And what you get is 3 kT times mc squared, speed of particles squared. Now, this is, by the way, resultant speed. So when it was 1 by 3, this is speed squared of any component. And when you remove this, this is the resultant speed squared. Anyways, notice one thing. Does this remind you of anything? Yes, it does. Remember, Ke is half mv squared. So to make this half mv squared or half speed squared, I'm going to divide both sides of the equation with 2. So that is how I get 3 by 2 kT is equals to half mv squared. So I can say kinetic energy of any particle is 3 by 2 Boltzmann constant times your thermodynamic temperature. Hence proven that temperature is a measure of kinetic energy. So when you have greater kinetic energy, your temperature will increase. Right. So when you have greater kinetic energy, temperature increases. Ke, kinetic energy, is only affected by temperature. Or you can say it the other way around as well. And my friend, that is all you need to know about ideal gases. And one last thing I'll add, this is the kinetic energy of one particle. Now when you have to find out the total kinetic energy of the entire system, you have to multiply it with n, that is number of particles. Then you'll find the total energy contained by the ideal gas. Now notice one thing, ideal gases will only have kinetic energy, no potential energy. Hence, PE is 0. So when they ask you to find the total energy of the system, you can simply do 3 by 2 times Boltzmann constant times thermodynamic temperature times number of particles there are. And you will find the kinetic energy of the system or the total energy of the system, right? The total energy of the system. Fair enough. That is all you need to know about ideal gases. This long derivation, you can try and understand again yourself, because this is going to be an important part for the exam. Anyways, we're going to now move on to the next part, that is, thermodynamics. Now, in this section, we're going to study about thermodynamics. In the previous case, you studied about ideal gases. With the same ideal gases, we are going to study thermodynamics. That is, we derived a bunch of formulas, right? Now, again, those derivations are very important. We derived how to get the kinetic energy of all particles, right? How to find the pressure in a system, right? And how we derived PV is equals to 1 by 3 NmC squared, right? All that. Fair enough. Now, in this case, we are going to consider working with this formula. That is, del U, change in internal energy of a system, is equal to heat transferred into the system plus work done on or by the system. Now, this entire chapter is all about sort of internal energy, working with this formula. And this is usually where really complicated and difficult questions come from. I've already made a video discussing and solving some of the hardest questions that I've at least seen come in the physics papers relating to thermal physics. And yeah, I'll link those in the description as well. But basically, in thermodynamics, you have to work with change in internal energy, providing heat, doing work done on gas, all that stuff. So your internal energy, if I want to define it, is the sum of random distribution of kinetic energy and potential energies within a system of molecules, right? It's the sum of kinetic energy and potential energy. But remember one thing, ideal gases do not have potential energy. At least we don't consider it to, right? So internal energy of any system is a measure of kinetic energy, only kinetic energy. And that kinetic energy can be changed by a few factors, by adding heat or by doing work done on the system. So that internal energy can be affected by two ways: doing work on the system, changing the volume, or adding heat, transferring energy into the system. So I can say that del U, change in internal energy, will only be done when I transfer heat into the system or I do work on the system. So Q is heat added to the system, W is work done on the gas. Now, potential energy is mostly changed when state changes occur. That is, when we were studying about temperature, we realized that in state changes, potential energy changes. However, when you're talking about just gases in the same state, there's not going to be much of any change of potential energy, even if you heat the system. So, your internal energy can be lost if heat is lost to the surrounding, right? Heat is lost to the surrounding, or let's say work is done by the gas, right? If work is done by the gas, even then you can lose internal energy to outside. Fair enough. So there are two ways. Let's say your del U, let's say your Q is 0. No heat is transferred into or out of the system. Let's say, and there is some amount of work done by the gas molecules. Let's say it's going to be 40 joules, right? How was the work done? So basically, there's a bunch of particles inside, and it moved the piston up by, let's say, 2 meters, or let's say 20 cm cube. Hence, the gas molecules did some amount of work on the piston, so it lost its energy. It lost its energy to move the piston. So work was done there. Hence, there is negative minus 40 over here, because work was done by your gas molecules on the piston. Energy was not transferred to the gas molecules. Hence, it is going to be negative 40. So the change in internal energy is negative, meaning internal energy was lost. What happened to internal energy? Internal energy was lost. Why? Because work was done by the gas on the piston. Now, internal energy and temperature. As objects heat up, the particles gain kinetic energy and vibrate faster. In reality, all particles experience some amount of intermolecular force. However, in our case, in ideal gases, we consider there to be no intermolecular forces. So, ideal gases don't have any potential energy, but they do have kinetic energy. Now, I can express that saying del U is going to be 3 by 2 K times del T times number of particles. So if I want to find the change in internal energy of any system, what will I do? I will take 3 by 2 K times whatever the change in temperature was. That is, let's say it went from 10 Kelvin to, let's say, 200 Kelvin. Whatever the change in temperature was, it is going to be proportional to your del U, right? Because internal energy is what? A measure of its kinetic energy, actually. And kinetic energy is a measure of its temperature, right? So, due to that proportionality, you can find the change in internal energy by finding the change in temperature. Because there is no potential energy, there is only kinetic energy. And I know Ke is 3 by 2 kT, right? So, that is why when you find the change in temperature and you multiply all of this with number of particles, that is, there's not going to be only one particle inside the container. There are going to be multiple particles. Hence, multiply that with 3 by 2 kT. And what you get is the total change in internal energy of the entire system. Of what? The entire system. So, that is how you get the change in internal energy. Right? the total change in internal energy. Now notice one thing. The only factor affecting your internal energy is going to be temperature. So in questions, when you see that the temperature has not changed, instantly you can say internal energy has not changed. Keep that in mind. Very, very important, right? Very important. So when you say the temperature is changing, when you see temperature is changing or increasing or decreasing, whatever, you know just off by that, internal energy must have been changed. What has happened? Internal energy must have been changed. Doesn't matter how, it has changed. You just know it. Fair enough. Now there's a question over here, but I'm not going to do it right now. I have a few questions done in the video. You can watch that. Now, work done by gas. How do you find the work done by gas? Probably you know it from AS, but work done is pressure times del V. Pressure remains constant and del V is the change in volume. So at constant pressure, whatever the change in volume is, let's say you decrease the volume of the container by 20 cm cube, right? You convert that to first meter cube and then do the calculation. So at constant pressure, let's say 2 pascals, you're going to multiply that with change in volume, let's say 0.02 meter cube, right? So now you know the work done on the system. So let's say you decrease the volume by 0.02 meter cube under a pressure of 2 pascals. This is your work done on the gas. So you transferred energy to the system. Fair enough. Okay. Fair enough. Now, first law of thermodynamics. The first law of thermodynamics tells you the same thing that we discussed. It tells you the increase in internal energy is equal to the energy supplied by heating plus work done on the system. Remember this. Why? Because 1 or 2 mark questions usually come in your paper 4. Asking you what first law of thermodynamics is. It's a common question. Anyways, the increase in internal energy is equal to thermal energy supplied or taken out plus work done on the system. Great. Now, in the case that internal energy increases, the heat should be supplied to the system and volume should be decreased. But either of those can happen to increase the internal energy. So del U, if you want the del U to increase, you want work done on the system or heat supplied to the system. So you can either decrease the volume and do work done on the gas, or you can supply heat to the system. By that, you can increase the internal energy as well. Now, if you want to remove internal energy from the system, what will you do? Either of two, that is, remove heat from the system, take heat out of the system, or increase the volume. That is, let the gas do work on the piston. Let the gas do work on the system. So either of those, if you let happen, that is going to decrease the internal energy. Fair enough. Now, these are the graphs for Boyle's and pressure law and Charles' law. You can take a look at it. I'll shortly explain. This is not that important as far as I've seen. So again, for the pressure and volume, at higher temperature, it is going to have a higher value of PV. So your product of pressure and volume is always higher, always higher, always higher, always higher, compared to the curve with lower temperature, right? Similarly, for Charles' law, at what happens is you're keeping the pressure constant. So when your pressure is constant, your volume for a lower temperature is less compared to volume of your higher temperature, compared to volume of higher temperature. Notice for the same pressure, your volume is greater. And for the same pressure with a lower temperature, your volume is lower. Now, pressure law again, for the same volume, notice at a lower temperature, let's say 400 Kelvin and 600 Kelvin. At a lower temperature, notice for the same volume, your pressure of higher temperature is greater. And pressure for lower temperature is lower for the same volume, right? So that is your pressure law. So that is all you need to know about thermodynamics. Again, if you want to understand how to solve questions relating to thermodynamics, which are usually very complicated, you can watch the video or watch other videos where they have discussed solving thermodynamics questions, because other than solving the question, you're not going to understand how to attempt those questions. These are usually the ones I see is quite tricky to tackle, right? So do watch solved questions or try solving the questions yourself to get a better idea of how to solve these questions, right? Fair enough. See you in the next section. Now, in this section, we're going to talk about oscillations. That is the 17th chapter. And I've made a full course in details about this chapter already available on my channel. So if you want the full details, you can check it out. And otherwise, you can just go through this crash course to get the relative idea. Now, the first thing is oscillation. What is the definition? It is a repeated back and forth movement on either side of any equilibrium position, that is the spin moving up and down about this equilibrium position. Oscillator, the spin is the oscillator that is moving. Now, what are the properties of oscillation? A, displacement. The displacement above or below the equilibrium position. Amplitude is x naught, or the maximum displacement from the equilibrium position. And angular frequency omega is the rate of change of angular displacement with respect to time. How is this angular frequency relevant? We're going to learn about that eventually in this chapter. Now, you may ask me that this pen moving up and down, where does angle come from, right? Where does angle come from? But when talking about the derivation, I'm not going to derive it, but I'm going to explain in short. You're going to understand where the angle comes into play. So wait. So angular frequency, you can express it as 2 pi by t, or you can say 2 pi f, because 1 by t is going to be frequency, right? Fair enough. Now, frequency is the number of complete oscillations per unit time. That is, how many times will this pen complete oscillation within 1 second, right? How many oscillation per unit time? That is your frequency. Time period is how long one oscillation takes. And for phase difference, it is the measure of how far an oscillation is in front or behind another oscillation. So it is measured in fractions of cycle or is measured in radians. So if you have two waves, so let's say these are the two waves. This is expressing displacement. This is expressing, let's say, time. And you're asking the phase difference between both oscillation. So let's say I have these two things oscillating. Notice the phase difference between both the oscillation. There is a phase difference of 90 degrees, right? There's a phase difference of 90 degrees, or say half of the cycle, or not 90 degrees. Call it a phase difference of, let's say, 180 degrees. Then you can say this oscillation that is going up and down compared to this oscillation is behind by half a cycle. So this oscillation is behind or has a phase difference of half cycle. So when this is moving down, this is moving up. When this is moving up, this is moving down. So there's a phase difference of 180 degrees or half a cycle. So if you have a phase difference of pi rad, you can say it is an antiphase, meaning it is traveling opposite to the direction of another oscillation. So this oscillation traveling opposite to this oscillation, right? So it is an antiphase. Now you can describe this phase difference in terms of radians, that is 180 degree, or you can express it in terms of cycle, that is, it is half a cycle ahead or behind, right? You can do either of those. Fair enough. Now, simple harmonic motion, the main part. What is simple harmonic motion? SHM is a type of oscillation in which the acceleration of a body is proportional to its displacement but acts in the opposite direction. Fair enough. So, in case of simple harmonic motion, basically anything that is in simple harmonic motion, its acceleration needs to be in the opposite direction to its displacement and has to be directly proportional. Meaning, let's say I have this bulb about equilibrium position. This, let's say, is positive amplitude. This is negative amplitude. And this is moving up, moving down, moving up, moving down, right? So at this position where it has a positive displacement, it will have a negative acceleration, meaning it will accelerate down, but its displacement is above the equilibrium. So it has a positive displacement, but at this point, it is going to accelerate downwards. Accelerate where? Accelerate downwards. Similarly, over here, it has a negative displacement, but it will accelerate up, meaning positive acceleration. This is what simple harmonic motion means, right? Fair enough. So your acceleration is directly proportional and opposite to displacement of the oscillator. Now, when you remove this proportionality, what you get is omega square. I have made a derivation video about it as well. If you want to understand, you can, but otherwise, since you're just a few days ahead of your exam, you can just remember this, that A is equals to negative omega square x, right? Fair enough. So this is the constant. Your angular frequency is the constant, right? Angular frequency. Okay, so that is the rate of change of angle, right? Fair enough. So where do you see simple harmonic motion? Simple harmonic motion is seen in a bunch of places. One is, let's say, pendulum, right? The pendulum moving right and left, right and left. That is simple harmonic motion. The other is mass on spring. That is, this mass is going to move up, move down about this equilibrium, right? This, if you let's say, move it down by 2 centimeters from its equilibrium position, from its rest position, it is going to oscillate up and down. That is simple harmonic motion as well. Now, deriving simple harmonic motion, I'm not really going to do. That is going to be very lengthy. But in short, what really happens is this. Notice this ball moving in a circle. Red ball moving in a circle, right? Moving around in a circle. That is circular motion. Uniform circular motion. But notice, if I shine a light from this direction, if I shine a light from that direction, I get a shadow projected over here. The blue is the shadow, the length of shadow. Notice as it moves in circles, the shadow length changes. If I consider this to be the equilibrium position, notice how the shadow changes. The shadow at 90 degrees, this 90 degree, why is this yellow? Yeah, the shadow at 90 degree is maximum, right? The shadow at 90 degree is maximum. Maximum displacement is seen over here. The shadow at, 180 degrees is 0. Notice the blue shadow. At 180 degree, it is 0. At 180 degree, it is 0. Right? Similarly, if I draw for all position, if I plot all the position, what I get at the end of the day is a curve looking like this. I have plotted the displacement against theta. Against what? Theta. The angular change. Right? The angle at every given position. So over here, this is 90 degree. This is 90 degree, right? This is 180, this is 270, and this is 360. So at every given position, if I plot the displacement against the theta traveled by this red bulb, I see that this is a curve similar to our sine curve. And I can say this is a sine theta curve. So my displacement y, I can express this as y is equals to sine theta. My displacement is changing with respect to sine of theta, sine of this theta. So in simple harmonic motion, my displacement is changing with respect to sine of the theta. Fair enough. So considering the displacement to be x, right, I'm just changing y as x. I can say x is equals to sine theta. And I can consider the amplitude to be a, that is the max. So I can plug in A over here because that is the amplitude, and you know before the trig function, the value represents the amplitude. So I can say x is equals to A sine theta. Now, the equation is in terms of theta, but the thing is, we don't want the equation to be in terms of theta. We want the equation to be in terms of time, right? What do we want? We want the equation to be in terms of time. Now, what do you know about omega? Try and remember. Omega is del theta, change in degrees, divided by change in time. So I can say the change in theta is equals to omega times del t. Can I say that? Yes, I can. Now, when you plug it in the sine theta formula, it is going to be x is equals to A sine omega t. This is how you get the displacement formula. This is how you get the displacement formula for simple harmonic motion, right? This is important, very, very, very important for the displacement of the oscillator at any given position. What is it going to be? You plug in the time, you know the angular frequency, it will be given, or you have to find it out, and you know the amplitude, right? Now you can find out its displacement at any given time. What is its displacement going to be, right? This is why this equation is very important, and this is how we find this equation. So I told I won't derive it, but I just derived it. But anyways, you can also consider it to be in terms of cos theta, but we don't, because for cos theta, you have to start from this position, that is 90 degrees. You're considering the displacement to be from max position, but we don't in general. So we always write in terms of sine theta. That is the standard. We don't consider the starting position of anything to be from max position. If you do, if the question tells you that it is starting from max position, then yes, your displacement formula will be in terms of A cos theta. But that doesn't really happen, so just remember this. Right? Just remember this. And if it starts from max position, amplitude position, that means it is the displacement formula is in terms of cos theta. Because at 0 degrees, at time t is equals to 0, your displacement is maximum. Right? That is why. Now, fair enough. In this case, when is the displacement A? Given that the angular frequency is pi rad per second, how will you find this out? You know that x is equals to A. That is, you know x is equals to A sine omega t, right? Now, they're telling you the displacement is maximum, or A. So, you can say A is equals to A sine omega t, right? So, you can cancel A off and you're left with 1 sine omega t. And they're telling you angular frequency is pi. So, you can now say that sine inverse of 1 is equals to pi t. And at the end of the day, what you get is the time is now going to be half seconds, because sine inverse of 1 is going to be pi by 2, right? Sine inverse of 1 is pi by 2. Yeah. Pi by 2 is equals to pi t. So pi cancelled off, t is equals to half. Right? This is how you're going to work with the formula, the displacement formula. Right? Fair enough. So by now you should understand properly that why the angular frequency is coming into play, because of this derivation. Great. Now, how to get the velocity? If you differentiate this, you're going to get this formula. That is, v is equals to v naught cos omega t. You can look at this and understand the derivation, but this is basically the formula. You just need to remember this formula, or you can differentiate in the exam paper and get the formula. So what you basically get is A omega times cos omega t. Now, what is A omega? A omega is basically going to be maximum velocity, because if you remember from circular motion, that your velocity is r omega, right? So when your r is maximum or amplitude, you're going to get the maximum velocity v naught, right? And when your radius is, your displacement is minimum, you're going to get the minimum velocity, right? So that is why A omega is v naught. A omega is what? V naught. Right? I explained it over here. So when your displacement is maximum, what you get is V naught. Okay. So now, when you draw this curve, notice the formula is V is equals to A omega cos omega t. I'm substituting A omega as we know, cos omega t. So when you draw this graph, it is going to be a cos function. It is going to be what? A cos function. Where the maximum, the amplitude is going to be V naught. And this is minimum velocity, I mean maximum velocity in the opposite direction. So fair enough, this is the graph that you're going to have for velocity. And with respect to this, this is the graph for your what? X displacement with respect to time. There is a phase difference of 90 degrees between the both. 90 degrees? Yeah, 90 degrees. So there's a phase difference of 90 degrees between the displacement versus time graph and velocity versus time graph. Right? When you differentiate any graph, it shifts, I mean any trig function, it shifts by 90 degrees. That is basically something you should know from maths. Anyways, so that is your velocity formula. Remember this. Now, moving on. How do we get to our simple harmonic motion formula? You're basically going to further differentiate this expression, right? And you get the acceleration formula. You can look at these steps and try to understand how we get the formula for acceleration. But basically, we get acceleration is equals to minus omega square x. That is the main thing, right? This is your main simple harmonic motion equation. When we differentiate the velocity equation, we get the acceleration equation. Fair enough. Now, when you draw the graph of acceleration, again, it is going to be shifted by 90 degrees. Shifted by 90 degrees. This is your 90 degree. What did I draw? 90 degree. Fair enough. So this is your acceleration graph with respect to time. A minus A omega square is your maximum acceleration, I mean in the opposite direction, and A omega square is your maximum acceleration in the positive direction. Fair enough. So this is another equation, that is, you've turned this into minus omega square x. So when after differentiating your velocity equation, you get this. And over here, what I had done is I turned this into x, because x, you know, is A sine omega t. So I substituted that value, or that expression over here, getting minus omega square x, right? So with respect to this graph, this equation, you can say that the amplitude is going to be A omega square, because it is in front of the trig function, and minus A omega square is your minimum value, but basically opposite direction. Okay, fair enough. So understand that how the graphs are going to look like. They might ask you to draw the graph, and that is going to be all the formulas. Now in summary, these are the formulas. X is equals to A sine omega t, V is equals to V naught cos omega t, and A is equals to minus A omega square sine omega t, or better known as acceleration is minus omega square x, right? Okay, fair enough. Now the part 4 of this chapter, that is position graph of simple harmonic motion. So up till now, we found all of the formulas, velocity, acceleration, displacement in terms of time. Now we are going to see it in terms of displacement. How does your acceleration vary with displacement? How does your velocity vary with displacement? That is what we are going to see. Great. So, you know the formula, A is equals to minus omega square x. Now this acceleration is in terms of displacement. Now if you wanted the acceleration to be in terms of time, this is your expression in terms of time for the acceleration. But if you want the acceleration to be in terms of displacement, this is your formula for acceleration in terms of displacement. Now, notice one thing, A is directly proportional to x, but the gradient is negative. Hence, it is going to be a negative gradient straight line through the origin. That is going to be your acceleration graph, right? When your displacement is negative, acceleration is maximum. When your displacement is positive, acceleration is minimum. That is opposite direction, right? This is what your acceleration versus displacement graph is going to look like. Now notice one thing, this is with respect to this pendulum. So notice at first position where the displacement is positive, the acceleration is in the opposite direction, that is leftwards. And in third position where it has a negative displacement, that is it has a negative displacement. Yeah, consider it to be a negative displacement, doesn't really matter. Where it has a negative displacement, it has an acceleration in this direction. So its displacement is left of equilibrium, but its acceleration is rightwards, right? So notice one thing, displacement and acceleration is always opposite, is always acting opposite. Hence, I can draw this graph that is with negative gradient, right? Respecting this equation. Okay, that is your acceleration with respect to displacement. Now, velocity against displacement, how do you draw that? This is your velocity equation, that is v is equals to plus minus omega x naught square minus x square. What does this mean? I have shown the derivation over here, but I'm not going to explain this in this video because I do have a separate video. If you want to understand, you can watch that. But the derivation is going to take some time, so I'm not going to show it over here, and that's not important or valid with respect to your syllabus, so I'm not going to talk about it. But basically, this is the velocity equation with respect to displacement, where the equation is telling you v is equals to plus minus omega root over amplitude square minus displacement square. X naught is basically amplitude. So you have to remember this formula. I don't know if it is given in the data booklet, I mean equation sheet. I don't remember. But anyways, this is your equation for the velocity with respect to displacement. So notice one thing, an equilibrium position, it is supposed to have maximum velocity. At this position, one position where it has maximum displacement away from the equilibrium position, it is supposed to have zero velocity because it will be instantaneously at rest in that position. In position 3, it is going to be again instantaneously at rest, right? At equilibrium, it is supposed to have maximum velocity. To express that in a velocity versus displacement graph, what I do is, in second position, that is in the middle, the velocity is maximum. That is, let's say, in this direction. And again, when coming back in the opposite direction, but in the equilibrium position, it is also maximum, but in opposite direction because its motion is opposite to initial motion, right? So maximum, but opposite direction, hence on the two axes. Now, its its velocity at the extreme ends, that is extreme right and extreme left. At that position, velocity as mentioned is zero. Hence, you get this ellipse, right? This oval shape. So this is basically, if you type this equation into a graphing calculator or Desmos, you're going to see this shape, right? So this is going to tell you that your velocity is going to vary as according to this curve, right? Now, to verify that, I can plug in a bunch of values and say, let's say I want to find the velocity when my amplitude is 0, right? So in that case, what's going to happen? V is equals to plus minus omega x naught square, which is my amplitude, minus 0, because I'm telling you that the displacement is 0. Sorry, not amplitude 0. Displacement is 0. That means in equilibrium position. So I'm going to get V is equals to plus minus omega x naught. Agreed? So plus is this value, minus is this value. So your equation is respecting both of them with the plus minus sign. That is why you have a plus minus sign, right? Fair enough. Now, the other one is extreme ends. So if I want to find the velocity at amplitude, what is it going to be? It is going to be velocity is equals to plus minus omega times root over amplitude square minus amplitude square, which is going to be 0. Hence, it is going to be V is equals to 0. At end of the day, your velocity is 0, right? And that is seen over here as well. At amplitude position or max displacement, the velocity is 0, right? Fair enough. Deriving velocity for simple harmonic motion. No, I'm not going to do that right now. You can check the video. That is not important. So now in the part 6, we're going to talk about energy graphs against position. Up till now, we talked about the velocity of acceleration with respect to displacement, or displacement, velocity, and acceleration with respect to time. Now we're going to talk about energy against position or displacement. Now in this case, notice for the energy against displacement graph at max position, that velocity v is equals to 0. Hence kinetic energy is 0. And again, minimum position for negative amplitude, the velocity is 0. And throughout the entire journey at mid position, the velocity is maximum. Hence kinetic energy is maximum. So what you get is this half circle. And that is going to represent your kinetic energy with respect to displacement, right? Fair enough. Now, the equation for kinetic energy is half mv square. Now, the velocity you can represent as plus minus omega root over x naught square minus x square. Now, this if you plug in to v square value, you're going to get omega square times x naught square minus displacement square. So now, when you take half m omega square x naught square common from the equation, when you simplify the equation, what am I saying? When you simplify the equation, what you're going to be left with is half m omega square amplitude square minus half m omega square displacement square. And notice the first half is a constant. Why? Mass doesn't change, angular frequency doesn't change, amplitude doesn't change. What changes is displacement. That is the only variable over here. Now notice, if your displacement is 0, that is at the middle position, your kinetic energy is maximum. So what you have is max Ke, because half m omega square times 0 square is going to be 0. So what you're left with is the first half of the equation. That is half m omega square amplitude square. Now when you take both of these omega and x naught together and put a power of 2 on both with a bracket, you notice this is r omega or amplitude omega or x naught omega, which is your max velocity, max v. Hence half m v max square. What does this tell you? Maximum kinetic energy. So your maximum kinetic energy is given by this expression, or half m v max square, right? By both, you're going to get the maximum kinetic energy of the particle. Great. Now, to get the potential energy, notice at the position 1, where it is at a maximum displacement away from the equilibrium, it has maximum potential energy because it is maximum distance above the equilibrium position. When it is at equilibrium, it is at the lowest position, hence potential energy is 0. And at, again, position 1 or position 3, whatever you want to call it, over there again, it has maximum displacement above equilibrium. Hence, its potential energy is again maximum. So you get a reverse, a U shape actually. So you get a U shape. This is your potential energy graph with respect to displacement. Okay. So now over here, notice something, that the total, if you want to find out your potential energy, you have to do it in a very interesting way. That is, your potential energy, that is total energy, is Ke plus potential energy. So I'm explaining it later on. First, let me show you the total energy graph. That is, the total energy, notice, is always constant. The object will never lose its total energy. It can transfer from kinetic energy to potential energy, but it won't lose its energy. So at this position A, it has maximum potential energy, but zero kinetic energy. So at this position, its potential energy equals to total energy. And at equilibrium position, notice there is no potential energy, right? The potential, I mean, there is potential energy, but it is minimum. Now, in this position, notice the total energy can be given by its kinetic energy, because at this position the potential energy is zero, right? Potential energy is zero. Why? Because it is at the minimum position, right? It is at the minimum position. Now, since it is at the minimum position, your potential energy is going to be zero, right? And at that position, kinetic energy is maximum, because it has maximum velocity in the equilibrium position, which is why its total energy at this point is exactly equal to the kinetic energy, right? So I can say total energy, let's say, since I know the kinetic energy formula and I know the maximum kinetic energy formula, that is half m omega square x naught square, that is the kinetic energy at this position. I can say total energy is TE is going to be half m omega square times x naught square. Can I say that? Yes, I can. Now, if I want to find the potential energy, I will say that half m omega square a square is equals to half m omega square a square minus half m omega square x square plus PE. This is your total energy. This is your kinetic energy as according to this equation. This is your kinetic energy. And this is your potential energy. Now, when you make potential energy the subject, what you get is both of these are cancelled off. And your PE turns out to be half m omega square x square, right? This is your potential energy formula in terms of displacement. Fair enough. So that is what we get. And these are the graphs. The graphs are important. The formulas are not important. You can derive it in the exam hall as well. But if you remember, that's great as well. But it's simple to remember because half mv square is the formula for kinetic energy. So instead of v, you're just replacing with omega x, right? That is it. So it becomes omega squared x squared. So for the maximum kinetic energy, it is x naught squared, right? Or for changing kinetic energy or kinetic energy at any given position, it is going to be half m omega square x naught square minus half m omega square x square, right? And the formula for potential energy is going to be this, right? Fair enough. So that is your energy formula with respect to position. Now, you also need to understand your energy formula with respect to time, right? Now notice one thing. The velocity equation with respect to time, how does it change? At max position, at equilibrium position, the velocity is maximum. Now, at position where it is maximum distance away from equilibrium, it is instantaneously at rest, as seen over here. Right? That is what we see in the velocity versus time graph. That equilibrium velocity is maximum. The moment you go to maximum distance away from equilibrium, velocity is zero. Now, when you draw the energy graph with respect to time, it is going to be slightly different in comparison to energy graph with respect to distance. How? Notice one thing. In case of your velocity equation now, v is equals to a omega cos omega t, right? Or you can call it v is equals to v naught cos omega t. So now your equation has changed slightly. So half m v naught square, or call it V naught cos omega t whole square, right? So this is now your equation for maximum kinetic energy. No, sorry, no, kinetic energy. What am I saying? This is your equation for kinetic energy, right? Now, notice one thing, that it is a cost function graph. Is a cost function graph. So, which one is K? Pink one. So notice it starts from the max position because cost function, and notice it doesn't go below the x-axis. Why? Because when you break or open this bracket, it is going to be V naught squared and cos squared omega t. Any trig function, if you square it, it is going to be in the positive axis. So notice the pink curve, it is cos square curve, right? This is your equation for kinetic energy. You don't exactly need to know that is extra, but you need to understand the shape of the graph. That is, in case of energy versus time, it is going to look something like this. For the kinetic energy, it's the pink one, right? And for the potential energy, when kinetic energy is, maximum potential energy is going to be 0, right? Potential energy is going to be 0. And it is going to alternate. When kinetic energy maximum, potential energy is 0. Right? So it is going to alternate in that manner. Now notice one thing over here, there is nothing called negative energy, which is why there is no value. There is no graph below the x-axis. Right? There is no value below the x-axis. Fair enough. So this is how your graph is going to be. So these are going to be your formula for kinetic energy and potential energy. Notice kinetic energy is half mv squared. If I plug in the expression for velocity, that is a omega cos omega t, or you can express a omega as v naught as I did above, and now the expression becomes either v naught squared, you can express this as v naught squared, or a square omega squared, and you have cos square of omega t, right? Now you know the maximum value of cos function or cos square function is going to be 1, right? So you can say the maximum kinetic energy is going to be half m a squared omega squared. Now in case of potential energy, it is again found out by saying the total energy is the sum of kinetic energy and potential energy, similar to what we did above. Now you don't need to understand this atrocity. I'm not going to ask you to understand this. This is not important, doesn't come in the paper, so I'm going to skip it. You can take a look at it to understand how the potential energy formula is derived, but otherwise you don't need it. Now this is also not needed specifically. But what you need is damping. We need to understand what damping is. Now damping, it is the reduction in energy and amplitude of oscillation due to resistive forces on the oscillating system. So damping basically means that eventually with time, your oscillation is reduced, meaning the energy is lost from the oscillation. So let's say pendulum, right? In our clock, what we do is we insert a battery to make sure the pendulum is penduluming. So in general, you don't really need to have a battery. If there is no friction force, if you release the pendulum, it is supposed to oscillate forever. But there are resistive forces. That is why you need extra bit of energy to make sure the pendulum is oscillating in simple harmonic motion. So that is why you need energy, because there is frictional forces, resistive forces. Now, if you didn't apply the extra bit of energy, damping would take place and the pendulum would stop moving. So you can try it out for yourself. You can displace the pendulum and see if it eventually stops. It will, obviously. So yeah, there are 3 types of damping: light damping, heavy damping, and critical damping. Light damping, what happens? There are more than one oscillation taking place. However, with every complete oscillation, the amplitude decreases. The amplitude decreases eventually. So a number of oscillations take place, and with time, slowly the oscillation ceases to 0, right? Oscillation would eventually become 0. So this is light damping. Now critical damping is when least amount of time is taken for the oscillation to return to equilibrium. So from max position to minimum position, minimum amount of time taken. So very fast it is critically damped. It is critically damped. So very fast, the equilibrium is reached. Returns to equilibrium in the shortest possible time without oscillating. For example, car suspension. Feature of displacement by time graph for a critically damped system. The oscillator does not oscillate. Its displacement directly falls to 0 in the shortest time. It has a very steep gradient, and at x is equals to 0, the line remains horizontal. So over here, it's not going to be asymptotic. It's going to meet the line, and yeah, that means that all energy has been lost. In heavy damping, it is just a linear version, that is, longer amount of time is taken for this to take place. That is, it's not the shortest possible time, but even in this case, from the max position, it is going to decrease to 0. It is going to reach equilibrium. No further oscillation takes place. So on the max position, it decreases to 0. And it takes a linear amount of time compared to critically damped system. In critically damped system, even in that case, it goes from max position to 0. So let's say if I displace it by this amount, it is going to critically damp and reach to 0. It is not going to move this side. It is not going to move this side. It is going to go from max displacement to equilibrium and stop. In heavy damping, it does the same thing, but in slower amount of time. It takes a longer period of time. That's it. So that is heavy damping. In light damping, what happens is, if it is oscillating with resistive forces, it is going to slowly oscillate. It is still going to oscillate, and eventually it is going to stop. Right? Just like that. Fair enough. Now resonance. Now understand one thing for resonance. Every spring, let's say you take a bunch of springs of different quality. If you displace it by an amount, it is going to oscillate. Displace all of the springs and see all of them are going to oscillate with different frequencies, right? Every object has a different natural frequency, right? So now if you take the same spring and displace it by 5 centimeter, it is going to oscillate with frequency f. If you now displace it by 10 centimeter, it is still going to oscillate by frequency f, because it's the same object. The frequency, the natural frequency, doesn't change. Now, what resonance is basically, whenever the natural frequency is matched by the external frequency, resonance is achieved. That is, let's say, I have a spring, right? And it has a certain natural frequency f. Now, I have an external oscillator that is making the object oscillate. So let's say I'm increasing the frequency of the oscillator such that it reaches natural frequency of the spring. So I'm going to increase the frequency of the oscillator to reach natural frequency, at which the oscillator's frequency and natural frequency is same, and maximum amplitude is going to be seen. Maximum transfer of energy from the oscillator to the spring will be seen. How? Notice one thing. First, a few definitions. Natural frequency is the frequency of an oscillation when oscillating system is allowed to oscillate freely. That means there are no resistive forces, there are no external forces. Free oscillation where there is no external force acting, hence no energy input. Energy is not lost, has no damping exist. Forced oscillation where periodic forces are applied to sustain oscillation. For example, the pendulum where you apply the battery, right? When oscillation is forced by external factors, then the frequency of the oscillator is known as driving frequency. So basically, the external factor that is giving the frequency of the spring or pendulum, let's say, that is the driving frequency. So I am driving the frequency of this pen, right? So I am helping it reach natural frequency or any other frequency. So I can choose the oscillator to make the spring oscillate at any given frequency. And when the frequency is natural frequency, resonance is achieved. What is it? Now, as understood, every object has a natural frequency. Sometimes we force objects to oscillate to overcome damping or the friction forces. When external forces are applied, the object will have a frequency known as driving frequency. So when you apply any sort of external frequency on the object to make it oscillate, that frequency that you apply is driving frequency. Now, when this driving frequency is the same as the natural frequency of the oscillator, resonance is achieved. Meaning, the object is going to have maximum amplitude. It is going to oscillate with maximum amplitude, right? So let's say this has frequency F and my hand is providing the driving frequency. If I match the exact natural frequency, it is going to oscillate with maximum displacement, right? Fair enough. Now, when this driving, fair enough, at resonance, energy is transferred from the driver to the oscillator most efficiently. That is, from my hand to the oscillating object, it is going to transfer the energy most efficiently. That is, no energy will be lost. Now, at resonance, maximum kinetic energy can be seen because, as seen with this example, that it has maximum amplitude, right? Maximum amplitude means it has a greater amount of velocity or greater amount of kinetic energy. Resonance, if you want a definition, it is going to be when driving frequency applied to an oscillating system is exactly equal to its natural frequency. The amplitude of the resulting oscillation increases significantly. So, when your frequency of the oscillating system and its natural frequency is matched, that is, the driving frequency you apply and its natural frequency is same, resonance is achieved, maximum amplitude is same. If I want to draw the graph is going to look like this. So let's say the x-axis is the frequency or the driving frequency, and this y-axis is the amplitude of the oscillator. Notice as I increase the frequency, the amplitude increases to a max point over here, to a max point over there. Notice one thing, this is supposed to be really, really sharp, meaning it is going to something like this. Something like this. So usually a blunt peak means that damping takes place, but a sharp peak means there is less amount of damping. Anyways, so this point is where maximum amplitude is seen, and as again you continue increasing the driving frequency beyond the natural frequency, even in that case the amplitude will decrease. The amplitude will what? Decrease. The maximum amplitude is only seen at natural frequency. So this is the natural frequency, right? Fair enough. How does damping affect resonance curves? So notice when you have least damping, the curve looks like this. When you have greater amount of damping, the peak shifts to the left-hand side, right? Shifts to the left-hand side. That is, your natural frequency decreases. This is the new natural frequency due to damping. Now notice when further damping is seen, the peak shifts to the left-hand side again. So as you increase the damping, the peak at which you'll see resonance, this peak at which you see resonance is going to shift to the left-hand side, right? So the natural frequency decreases, right? Fair enough. So if you extend this line, you're going to see resonant frequency for highly damped oscillation, right? So that frequency at which resonance will take place is going to eventually decrease. Fair enough. So if you have a even more highly damped system, let's say this, it needs an even lower frequency to achieve resonance because its natural frequency has decreased. So this is how your graph is going to look like. And that is it for simple harmonic motion or oscillations in general, right? So I would recommend you watch these two videos, that is simple harmonic motion in pendulum and simple harmonic motion in spring. I have it available on my channel. You may find other videos as well. So you'll get a better idea of how the calculations work and how to find time period, but it is not exactly necessary. But I'll still give you a small hint, that is, often they'll give you equations such as, let's say, they're going to give you that A is equals to minus K by M x. They're going to tell you that this is the equation for acceleration of, let's say, a spring. Is it a spring? Yeah. So let's say they're going to tell you this is the acceleration equation for the spring. Now they're going to ask you to find out the angular frequency, right? They're going to ask you to find out the angular frequency. What do you do? Or they're going to ask you to find out the time period. What are you going to do? Notice this and this is same, right? Minus omega square is the constant, and over here minus K by M is the constant. So you're going to say omega square is K by M, and you're going to say that 2 pi by T whole square is K by M. Now make T the subject, time period the subject, and what you get is 2 pi times root over M by K. And now when you plug in the mass value and K value, you're going to find the time period. This is how you deal with different acceleration formulas given in the question, right? And that is going to be your oscillation. Now let's meet in the next section. Now the next topic is going to be electric fields, and we're going to start off with this chapter by talking about Coulomb's law. Now, a few things to understand is for 2-point charges, if they have the same or different sign, they will feel a force due to the presence of each other. So if you have a positive charge and another positive charge, they're going to repel each other. So they feel a force due to the other charge. So when there is any sort of charge interaction, there will be a force exerted on each other. Just like gravitational force, even in this case, the force exerted on the both charges, point charges, is going to be the same. That is, whatever force Q2 applies on Q1, the same force will be applied on Q2 by Q1, right? So the forces are always going to be equal. Now for the Coulomb's law states that the force is directly proportional to the product of charges and inversely proportional to the separation of the charges, right? This. And when you remove the proportionality, you get a constant K. Now what is this constant? This constant is basically 1 by 4 pi epsilon naught. This part we understand. What is epsilon naught? Epsilon naught is another constant that is basically permittivity of free space. Consider it a property of material that measures the opposition it offers against electric field. So whenever electric field is built, it is a measure of how much that material is going to oppose that. Or the other way to think about it is a tendency of materials atomic charge to distort when the material is placed in a electric field. So in both cases, what both these definitions are saying is it is a sort of resistance when in the presence of electric field, right? So consider this as a sort of resistance when in the presence of electric field. For different mediums, the permittivity is different, but this is a constant in our case. We're going to consider the permittivity given in our data sheet, which is going to be I don't know the exact value, but this whole value of K constant is 8.99 into 10 to the power 9. You can check the value of permittivity of air or free space. Something's written on the data sheet. So you'll know the value of epsilon naught, right? So this part is a constant. Great. Now, ultimately, my formula is going to be force is equal to product of charges divided by 4 pi epsilon naught separation squared. So the separation between two charges. Fair enough. So this is your Coulomb's law. Force between 2-point charges is directly proportional to the product of their charges and inversely proportional to the square of their separation. If you plot the graph of force versus distance, it is going to be an inverse square graph, just like 1 by x squared. Great. Moving on. What is electric field strength? Electric field strength is nothing but the force with respect to 1 coulomb of charge. So in the main formula where you have F is equals to KQ1 KQ2 divided by R square, over here you're going to plug in, let's say, the value of Q2 as 1. So you're measuring the electric field strength of Q1. You're measuring what amount of force will Q1 apply on 1 coulomb of charge at different distances, right? So that is how you get the electric field strength formula of any charge. So if you're measuring the electric field strength formula for charge 1, this is the formula. If you're measuring the electric field strength of charge 2, it is going to be E2, electric field strength 2 is Q2 divided by R square. So at any separation distance away from your charge Q2, what is the electric field strength going to be, right? How much force will Q2 apply on 1 coulomb of charge at any given distance? Great. Now, how are electric field lines expressed? When you have uniform field lines, that means that electric field strength at this position is exactly the same, meaning uniform distance, meaning field strength is uniform, meaning strength of force applied is same throughout this region. Over here, ununiform. Why? Because over here the field lines are crowded, meaning greater force over here, greater electric field strength over here, and less electric field strength over here. Now, for point charges, for positive charge, the charge is always outwards. Why? Because whenever you bring a positive charge near another positive charge, another positive charge, it is always repelled, always repelled, always repelled, always repelled. Now, when you have a negative charge, the force is attractive. The field lines are attractive. So when you bring a test positive charge, it is going to be attracted. It is going to be attracted, right? Hence, the field lines for negative charge is inwards, right? We always think of field lines with respect to a test positive charge, So a test positive charge is repelled by a positive charge and attracted by a negative charge. Hence, your positive charge will have field lines outwards, and negative charge will have field lines inward, right? So when you connect these field lines, it is going to look like this. As you move away, the distance increases, right? As you move away from the charges, the distance, the field strength is going to decrease. Notice the distance has increased between the field lines, meaning the field strength is less at a position with greater distance away from the charges, right? Fair enough. Now, electric potential energy. What is your electric potential energy? It is the work done in bringing a charge from infinity to a defined point in electric field. Similar to gravitational field strength, gravitational potential energy, it is defined as the amount of work needed to bring any charge, a test positive charge, from infinity to a defined point. So if I have charge Q1 over here and I am analyzing its electric field and I have a test positive charge Q2, consider this to be a positive charge and consider that test charge to be positive as well. If I bring Q2 from infinity to a defined point R, what is the work done going to be? It is going to be positive work done. Why, you ask? Because I'm overcoming repulsive forces. Between Q1 and Q2, there is repulsion. Why? Both of those are positive. Hence, repulsive forces, which is why I have to overcome repulsive forces. Hence, I have to do work on this charge. So, positive work is done. Hence, this when I will be drawing the electric field strength, when I will be drawing the electric potential energy graph, you'll notice for this same graph, the potential energy graph will also be on the positive axis. On what? The positive axis. Why? Because positive work is done. This is, by the way, the force versus separation graph, not the potential versus distance. It is sort of similar. The potential is going to be somewhat like this, right? Consider this to be the surface of the charge, and this is going to be your potential energy graph, a bit less steep. That's it. Why? I'll explain it later on. Now notice one thing, that in case of repulsive forces, due to repulsive forces, work done is positive in case of positive charges, right? So when you have two positive charges, repulsive force, hence work done is positive, hence on the positive axis. In this case, notice the force is 1 by r square. F is proportional to 1 by r square. So the force curve looks like this, right? So now bringing it from, this is r and this is infinity, right? So this is a point r1 and this is infinity. So electric potential energy is telling you the amount of work done in bringing the object from infinity, not the object, sorry, the charge from infinity to a defined point r. So this area under the force curve is going to be your total work done in bringing from infinity to defined point r. Fair enough. Now, I'm not going to prove this formula, but basically your electric potential energy will be given by U is equals to KQ1, KQ2 divided by R, right? So K times product of two charges divided by separation. This is going to be your electric potential energy, right? Fair enough. So the work done in bringing Q2 from infinity to a defined point near Q1. This expression gives you the electric potential energy. Now, how do you find the change in electric potential energy? Similar to gravitational field strength. You're going to take Q1 and Q2 out of this expression, take it, factor it, and what you're left with inside is 1 by R1, consider it to be the final position or initial, doesn't really matter, and 1 by R2. So I'm considering R1 as the smaller value and R2 as the larger value. Hence, at the end of the day, my change in electric potential energy is going to be positive. Why? Because I'm actually bringing it closer to charge Q1. Hence, I'm doing positive work on the object, which is why I've taken the smaller value over here and a larger value over here, such that my ultimate answer is positive, because my change in energy is positive. Positive work has been done, right? So this is your expression for change in electric potential energy. So whatever the change in distance is going to be, you plug it in over here, 1 by R1 minus 1 by R2, and you're going to get the change in electric potential energy. Now, what does having positive or negative electric potential value mean? When you have repulsive forces, it is going to be positive electric potential energy, because repulsive forces, it is going to, both of those are going to repel each other. So the work done is going to be positive. However, when you have attractive forces, that is one positive, one negative attractive forces, hence the potential energy, change in potential energy is going to be negative, right? When bringing it closer together, in the case that there is attractive forces, in that case, the EPE or electric potential energy is negative. Remember, from gravitational potential energy, they have attractive forces. Hence, when you have attractive forces, your potential energy is negative. Is what? Negative. Right? Great. So now your electric potential, how do you find out the electric potential? It is basically the same as electric potential energy, just you're going to plug in 1 coulomb of charge instead of Q2. So you're analyzing the electric potential of Q1, right? You're analyzing the electric potential of Q1. That is, how much work will be done on 1 coulomb of charge, in bringing it from infinity to a defined point R in the presence of Q1. In the presence of Q1, if I bring 1 coulomb of charge from infinity to R, what is the work done? That is your electric potential. That is your electric potential. Fair enough. So your electric potential value turns out to be KQ1 divided by R, where K is basically 1 by 4 pi epsilon naught, right? Fair enough. Now, how do you find the change in electric potential? Very simple. You just consider Q2 to be 1. Hence, KQ1 and the rest of the formula remains exactly the same. So that is your change in electric potential. Now, plotting the V by R graph, that is potential versus distance. So you know the formula. Potential energy electric potential is going to be KQ1 divided by R. Notice your voltage or your electric potential is inversely proportional to separation. Why did I call this voltage and why am I writing V? I'm going to explain it later on. But first, let me tell you this, that when you plot electric potential versus distance, what you get is a 1 by x curve. Exactly this. Asymptotic over here, asymptotic over here. But it is not going to be asymptotic over here exactly, because at this point, consider it to be the surface of the charge. And inside the charge, it is going to be constant. Why does that happen? I'm going to explain it later on. But for now, understand from R to infinity what the shape is going to be, right? Fair enough. So now, why is it known as electric potential as voltage? Basically, what do you know voltage to be? Voltage is work done per unit charge. Work done per unit charge. Now, due to that, we can also call electric potential as voltage, right? Because your electric potential definition is exactly the same. The formula is exactly the same. The amount of work done in bringing 1 coulomb of charge from infinity to a defined point. Hence, voltage also says the same thing. Work done per unit charge, which is why you can call electric potential as voltage, right? As voltage. And this is going to be your graph for voltage against separation, right? Fair enough. Now, let's find out how to get the electric field strength from the potential graph. That is, the basic idea is whenever you find the gradient from a potential graph, you also get the electric field strength. This is your EFS. This gradient at this specific point is going to give you the electric field strength. That is, the gradient of a voltage or electric potential versus separation graph is going to give you your electric field strength. Why does that happen? Notice one thing. When you have a force, and distance graph, the area under the graph is EPE, electric potential energy. Similarly, when you have a electric field strength graph, let's say this, with respect to distance, the area under the graph is going to give you EP, or electric potential, right? The voltage, work done per unit charge in bringing it from infinity to a defined point. Now, since this area under the graph is is electric potential, I know integrating electric field strength gives me electric potential. Understand carefully. Integrating electric field strength gives me electric potential. So, if integrating my electric field strength gives me electric potential, doesn't that mean if I differentiate the reverse operation, if I differentiate my electric potential, shouldn't I get electric field strength? Yes, you do. So when you have your electric potential curve, whenever you find the gradient at any given point, at any given separation, this, or this, you're going to find the gradient, and that is going to represent the electric field strength at that specific point. Notice the slope decreases as you move away. As the radius increases, the separation increases, your slope decreases, meaning your electric field strength decreases. Now let's see how to get that electric field strength, right? So this is your typical voltage formula or electric potential formula. Now when you take a derivative on either side, when you differentiate either side, what you get is KQ1 by R turns out to be minus KQ1 by R square. So if you differentiate it, you're going to get this expression, this, right? If you differentiate this, it becomes this. Fair enough. So on this side, dV by dr is basically small change in V divided by small change in R, right? So the gradient of the voltage and distance graph. So notice one thing, when I take the negative sign over here, I get electric field strength on this side, on the right hand side. KQ1 by R square is basically my electric field strength formula. So I get electric field strength is equals to the derivative of my potential curve, right? Now, electric field strength is the negative derivative of my potential curve. That is what I get. The negative derivative, the negative gradient of an electric potential and distance curve will be able to give you the electric field strength. So whenever you find the gradient over here, this is going to tell you what the electric field strength at this position is going to be. Fair enough? Fair enough. Now, understanding electric potential around a charge. Whenever you have a positive charge, notice it is going to have fields that is outwards, right? So since the field is outwards, it is going to have a potential that is positive. That is what? Positive. Why? Because it's a positive charge. Fields outward. Now, whenever you bring in a positive charge near another positive charge, notice it is going to be facing repulsive forces, which is why work done is positive, hence it is on the positive axis, right? Notice this is how we plot the curve. Notice how with distance potential decreases. And in case of negative charge, near the surface it is maximum. Near the surface it is maximum. And as you move away, it decreases. But the entire curve is now in the negative axis. In what? The negative axis. Why, you ask? Because whenever you bring a positive charge near a negative charge, attractive forces, hence your potential is negative. So negative. Positive one, it's going to be on the positive axis. Fair enough. This is how the graph is going to be, right? Fair enough. Now, electric field strength in uniform fields. Notice my del V by del D, that is gradient of a electric potential curve, is going to give you electric field strength. Similarly, when you have, a uniform electric field, that basically means that over there is no variation of electric field strength. Electric field strength is constant, meaning whenever you find change in del V divided by change in distance, so whatever distance there is over here and whatever the potential difference between these 2 points is, when you divide both, you get electric field strength. So let's say I have this plate of 0 voltage and this plate of 20 volt. So what is the electric field strength between these plates? It is going to be 20 divided by, if the distance is 2 meters, 2, and my EFS is going to be 10, right? 10. So the unit of this is going to be either Newton per coulomb, that is force per unit charge, or voltage per meter. You can write the unit of electric field strength as either. Both are accurate, right? Why volt per meter? Because of this formula. And why Newton per coulomb? Because force per unit charge, right? Fair enough. So that is how you find the electric field strength in case of uniform fields, right? These are uniform fields. So over here, whatever the distance is, that is going to be del D whatever your potential difference is, that is your del V. And this is your EFS, electric field strength. Now, for spherical conductors, this is where the graphs are going to come into play. So, first up, let's understand how spherical charges behave. For spherical charges, notice this is a sphere of charge, right? And there's a bunch of positive charge inside stored. But what usually happens if it is a good conductor, in that case, the charge is going to settle on the surface. It is going to move away from each other and equally distribute itself on the surface with equal distance from each other, right? To make sure they're the furthest apart from each other, right? Great. Now, what you next notice is for positive charges, the fields are outwards, right? Fields are outwards. So these fields, notice, are radial. So these seem to meet exactly at the center, which is why I can consider this to be a point charge, meaning this point to be the center, right? This point is from where I'm going to consider the separation of another point charge to be, right? Fair enough. The electric field for a spherical conductor, the electric field lines are radial and perpendicular to the surface. Notice it is normal to the surface. The lines are outwards for a positive charge, since if another positive charge is brought in, it would be repelled, hence pushed outwards. The electric field strength versus distance graph for spherical charges. Notice one thing, for the force versus distance, your electric field strength is directly proportional to the inverse of separation square. So as you move away from the charge or sphere, your electric field strength decreases by 1 by r square amount. And inside the sphere, notice, there is no net force. Why, you ask? Because notice, at this position, let's say, random position, if I draw a line, notice, there are multiple charges over here, but at a greater distance away from this point. There are less charges here, but at a closer distance to this point, right? So let's analyze these two places. These charges, although greater in amount, they're farther away from this point, which is why they're going to have a force on this position, let's say x Newton. However, there are fewer charges over here, but it is closer to this point, which is why this is also going to apply x Newton of force on this point, since it is closer, although less charge, but closer. Hence, same amount of force is going to be applied on this point in two different directions. Same thing is happening in this case and this case, which is why at the end of the day, there is no net charge inside the sphere at any given position, because the charges, forces, cancel each other out in opposite direction. That is why inside the sphere, electric field strength is 0. Electric field strength is what? 0. Fair enough. So this is how your electric field strength versus separation curve is going to look like. Inside 0, and from the surface, that is radius, from the surface till infinity, it goes like this, 1 by r square. Next, electric potential versus distance graph. Notice electric potential inside the graph is constant, and as you move away from the away from the sphere, it is going to decrease. By what factor? 1 by r. So, with respect to 1 by r, the curve is going to be of this shape. That is, the electric potential decreases with increasing distance. Now, you will ask me, why is the electric field strength inside, why is the electric potential inside constant? That is because, notice one thing, guys. If I show you over here, if I bring a charge, let's say this charge, from this point r infinity to this point, I'm doing what amount of work? I'm doing some amount of work on, let's say, the repulsive forces. Consider this red charge to be positive as well. So I'm doing some amount of work to reach the surface of the, what do you call it? Positive sphere. So I'm doing, let's say, 30 joule of work on this positive charge to reach the surface. However, after I reach the surface, it is constant. Why? Because inside the sphere there is no force. So the moment I cross this line, no more amount of work is done on this test positive charge. Because after I reach or transfer 30 joule of energy, no more energy needs to be transferred to this test positive charge. Because inside the sphere, notice, inside the sphere, there is no electric field strength. Hence, inside the sphere, it is going to be constant. It is going to be what? Constant, right? So that is why you see a constant line over here, a straight line inside the sphere. Now you're going to ask me, why is this in this manner? That is, why is this going to be 1 by r? The other way to explain it, other than this 1 by r proportionality, is by thinking about the gradient. So your negative gradient of this is going to be the value of your electric potential. So let's say this, right? This is going to give you a negative gradient. However, as mentioned, minus dV by dr is your electric field strength, EFS. Hence, minus of a minus gradient is going to be ultimately a positive gradient. Hence, your electric potential is positive and is going to respect this 1 by r proportionality, right? So this is going to be the shape of electric potential curve. Great. What did I say over here? Okay. Fair enough. Now the important part are the graphs. We're towards the end of this chapter. So the resultant potential and electric field strength curve of two opposite charges. So let's say I take a positive charge and I take a negative charge. Notice both of these are oppositely charged. What sort of force acts over here? Attractive force, right? Attractive force is going to act over here. Hence, notice if I draw the potential curve for this, first let's draw the field strength curve. Later on, I'm going to draw the potential curve. So first one, electric field strength. For the positive charge, notice at the surface, the electric field strength is maximum, right? At the surface, electric field strength is maximum. This one. And as you move away from the positive charge, it decreases. It does what? It decreases, right? Now, I want to find the resultant electric field strength due to both of these charges. So I also draw the electric field strength curve for the negative charge. Notice for this negative charge, the field lines are inwards as well. So the positive charge has a field line that is in this direction. The negative charge also has field lines in this direction. Hence the direction is the same for both charges between this region. Hence both are on the positive axis. So the negative one, notice the field lines are inwards, at least for this region. So at the surface of the charge, it's going to be maximum. As you move away from the surface of negative charge, decreases. And when you add both of these curves up, both of these, you get this pink curve. That is going to be your resultant electric field strength in this region. Now you can do the same for this region and this region. Fair enough. So again, one more thing. Inside the curve, it's going to be 0. The field strength is supposed to be 0 inside the curve, right? Inside the curve, field strength is 0. Inside the curve, the field strength is 0. Sorry, inside the sphere, the field strength is 0. Right, inside the positive sphere, field strength is 0. Inside the negative sphere, the field strength is 0. Right, so you draw the field strength curve for positive charge, you draw the field strength curve for negative charge. And then when you add both the values up, you get the resultant curve, right? This resultant curve. Fair enough. So that is your electric field strength versus distance resultant curve between unlike charges, right? Now, if I draw the potential curve, what's going to happen? Notice one thing. If I draw just the positive one, notice inside constant and maximum, as you move away, it decreases, right? For the positive one, for the positive charge, it's supposed to be on the positive axis. Why? Because field lines are outwards, right? Field lines are outwards. Fair enough. Now, this value is going to be positive, right? So for the positive one, it is on the positive axis, since it is a positive charge. Now, notice one thing. For the negative charge, the field lines are inwards, right? Field lines are inwards. And for negative charges, notice the work done is also negative, which is why it is on the negative axis. For positive charge, if I bring a test positive charge, repulsive forces. So the work done is always positive, be it this side of the curve, be it this side of the curve. Whenever I bring a test positive charge near a positive charge, what happens? Repulsive forces. So positive work done. Hence, unlike the field strength curve where the direction of field line matters, in potential curve, your direction of field line doesn't matter. What matters is the nature of charge. If it is a positive charge, it's going to be on the positive y-axis. If it is a negative charge, it is going to be on the negative y-axis, because negative charge means negative work done. Positive charge means positive work done in terms of a test positive charge. If I bring a test positive charge, repulsion, hence positive work done. If I bring a test positive charge over here near the negative charge, attractive, hence negative axis. Great. Now, when you draw the curve, this is going to be your electric potential curve for the positive one, and this is going to be your electric potential curve for the negative one, right? At the surface, maximum but negative. Inside, it is constant and maximum. And as you move away from the negative charge, the value reaches 0, right? Now, when you sum both of these up, graphs up, what you see is this slanted S curve. Meaning, when you add both of these up, you get a point where electric potential is 0. Electric potential at this point is 0. So, this is your resultant electric potential curve between two charges, between two unlike charges, right? Now, you may ask me, why is the electric potential 0 at that point? In brief, what happens is, if you bring a positive charge from here, you have to do positive work done. Now, at the moment you release this positive charge over here, it is being repelled by the positive charge and being attracted by the negative charge, which is why it falls down. It loses all its energy because of the attractive force of this negative charge. Because of the attractive force of the negative charge, notice negative charge, the potential eventually decreases to 0. Resultant potential decreases to 0. Whatever work I did on this positive charge to bring it near this positive charge, it lost all its energy due to this negative charge. It lost all its work done due to the attractive force, right? Hence, at the middle, the electric potential is 0 between two unlike charges. And you will often be asked to find this point. That is, where is the electric potential, resultant electric potential 0? And what you will do is, you'll find the electric potential of the positive charge and the electric potential of negative charge, and you will equate both together. So electric potential of positive charge plus electric potential of negative charge is equals to 0, right? the resultant electric potential is supposed to be 0. Hence, you're going to write KQ1 divided by R minus KQ2 divided by R is equals to 0. Now you're going to find the distance, right? Fair enough. Now, often what you have to do is you're not going to write R over here. You're going to consider this distance, let's say X, and often they'll give the separation value. So let's say the separation is given as 20, and you're going to say X is the distance away from the positive charge. So let's say for the positive charge, I'm going to say KQ1 by X, and for the negative charge, I'm going to say 20 minus X, right? And now I'm going to solve for X and find the distance where the resultant electric potential is 0. So I'm going to find X. Right? So you will find similar sums in the question paper. And when you do those, you'll understand better what I'm saying. So basically, add the electric potential formula of both charges and equate to 0. You will find the distance at which this point, at which the potential is 0. Okay, fair enough. Now, what happens when you have unlike charges? If you draw the positive one, that is the yellow one, notice from the surface to infinity, it decreases. For the negative one, notice right now the electric field strength is outwards for the positive charge as well, right? Electric field strength is what? Outwards. Both of these opposite direction, which is why for this positive charge, it is in the negative axis. Why? Because in case of electric field strength, the direction matters, which is why for this positive charge, it is in the negative axis. Why? Because direction is leftward. For this, direction is rightward. Hence, for this positive charge, it is on the positive axis. For this positive charge, it is in the negative axis because opposite direction. Now, after you draw this electric field strength graph, when you find the resultant, you're going to see at one point the resultant is again 0. In this case, electric field strength is 0, not potential. In case of like charges, electric field strength is 0. Why, you ask? Because at this point, it is feeling the same amount of force from this charge and the same amount of force from this charge. So both of those are equally pressing on this position. Hence, over there, the net force is 0. Both cancel out and net force is 0. So over here, you see a resultant 0. So when you find the resultant curve, it is going to be something like this, right? And when you find the potential, it is going to be somewhat like this, where, notice one thing, inside the potential of the positive is maximum and constant. Inside the positive one, again, it is maximum and constant. Now notice, both of these are positive charges. Hence, it is on the positive axis. In electric potential, what matters is the nature of charge. In electric field strength, what matters is the direction of fields, based on which you're going to draw the graph, right? Which axis are you going to draw the graph? Depending on the direction of the field lines, right? Positive, if let's say this direction you consider to be positive, so on the positive one, and this opposite direction you consider to be negative, so for this charge, it's going to be on the negative axis. Simple. So field strength, consider the direction. Potential, consider the nature of charge, right? So now, when you sum both of these up, you get this resultant U-shape curve. That is your resultant potential energy. Notice, potential energy over here is never 0. Why? Because you always have to do some amount of work when you're traveling from this direction to up till this point. You're always doing some amount of work, right? Over here, at no given point is there attractive forces, which is why that energy is not going to lose to 0. Yes, at some point, that is from this position, that is surface of the positive one, it is going to be repelled. It is indeed going to be repelled, which is why it does decrease. However, it again starts increasing. Why? Because repulsive forces of this positive charge, right? That is in theory what's happening, why there is a minimum and why we see a maximum in both of these ends. But if you understand the graph, if you can remember the shape of graph, I would recommend obviously understanding how the graph is drawn. So if you understand the nature of this graph, y positive, y negative, how is the potential going to be drawn, how is the electric field strength going to be drawn, if you understand that, you're good to go, right? And the last thing is motion of charged particles. Now, in case of motion of charged particles, if you have two plates, one positive, one negative, and you launch a positive charge inside, it is going to form a parabola. It is going to form a what? Parabola. Why? Constant amount of force is there throughout the entire space. So consider it to be, let's say, in AS you've studied in kinematics, I guess, projectile motion. So if you launch a ball from here, it is going to, reach the ground as a parabola, meaning there is constant force on the ball, that is gravity is acting on it, that is 9.81, and the weight is always constant, pulling it down. Similarly, same amount of force is always pulling it down throughout the journey, which is why it forms a parabola, right? And similarly with the negative charge, it is going to be a parabola, but it is going to move towards the positive plate. Now, there are a few factors to consider for this deflection. Now, whenever you have a larger mass, the deflection is going to be less. Or whenever the deflection is less, the mass is larger. Why? Inertia. Fair enough. When the charge is greater, deflection is greater. So when you have a greater amount of positive charge, it is going to be greater repelled by this positive plate. Great. Now your speed is going to be inversely proportional to deflection. That is, when you have a greater speed, the deflection will be less. Why, you ask? Because it will spend less amount of time between the charged plate, which is why the deflection you see will be lower, right? That is why the speed is inversely proportional to deflection. Fair enough. And that is going to be it for electric field strength. Electric field strength. And one more thing I want to add over here is they're often going to ask you to draw these circles, that is to represent the field lines in the sense that how strong are the field lines as you move away from the charge, right? So notice near the charge, it is strong, meaning you draw two concentric circles, that is these two circles are closer to each other, and as you move away from the surface, from the charge, it is going to be further apart, it is going to be further away, right? This distance is greater than this distance. That means what that basically means is, if I find the exact, yes, so for this one, notice for the same decrease in potential, you travel a small distance over here. The potential fall is 5 volts, a small distance. Now, for the same 5 volts to drop, you have to travel a much larger distance, right? Now notice, again, for the same 5 volts of drop, you have to travel a much larger distance. Notice, a much larger distance. So they'll often ask you to draw circles around the charge to represent how the electric field strength changes with changing distances, or how electric potential changes with changing distances, right? Fair enough. And that is going to be it about electric field strength, and see you in the next section.